Okay, so it's an honor to present Danqi Chen. She is computer science professor at Princeton, where she also is associate director of the Princeton Language and Intelligence Initiative. Um, her research interests span a large set of topics, but particularly large language models and simple strategies that scale up is one of her main topics, and she's here to lecture us about transformers and pre-trained language models, which is a topic that needs no introduction. So very excited to have her presenting this.
Can you hear me? Okay. Okay, thanks for the introduction, and thanks for joining me this morning. It's actually my first time being here attending this summer school, and also actually first time visiting Portugal. So it's really lovely to be here. Actually arrived here last night, so pretty last minute, yeah. Okay, so today the lecture I'm going to talk about is on the probably topics everyone cares about, transformers and large language models. Since it's my first time being here, in case if you are not familiar with me, here is just a brief introduction. So I'm Danqi Chen, and I have been a faculty at Princeton University for almost 5 years now. I lead a research group of almost 10 graduate students. So today I will touch on a little bit of the research works we have been doing and thinking about over the years, but not too much in depth. So a lot of research we have been focusing on in the past few years has been on the large language models to think about how to train and adapt, and also more important, how to understand the current large language models. So if you're interested in learning more about our research, so feel free to check out my website, and there'll be a lot of papers and GitHub repos and a lot of information there. Okay, so since this is one of the a morning lectures, so it'll be a 3-hour lecture. So I divide the lecture into 2 parts. The first part, I will focus on transformers. So the focus will be on the innovations and also the key design choices in these neural architectures. And in the second part of this lecture, I will focus on the pre-training, the pre-trained large language models. I will mostly focus on the training objectives, training data, and how to adapt the pre-trained large language models to different user needs or different applications. And there'll be a 30-minute break in between, so I think there'll be a nice split here. Again, since this lecture will be mostly focusing on the fundamentals of these ideas, so I'll just give you some expectation. So this lecture, my design will be 70% will be on the fundamentals of these topics. So I will really walk through some of probably the most important ideas in NLP and large language models in the past 5 years, including transformers, BERT, T5, GPT models, pre-training, context learning, RLHF. If I believe most of you are already doing research in NLP or NLP large language model practitioners, so I'm sure that you are more or less already familiar with concepts. So my hope is that I can try to delve into details a bit more, and then really try to have a more in-depth understanding of these concepts. But I only have 3 hours, so we'll see what we can learn in these 3 hours. But if you're not familiar with this concept or topics, and if I go too fast, feel free to just interrupt me and ask questions. I also don't have to finish all my slides. And this 70% on the fundamentals of these topics. And for another 15%, my hope is that I will start with these most important papers, the seminal papers, but I'll also highlight how these fundamental ideas have been evolving over the past 5 years. I will highlight some of the recent improvements and developments, and hopefully you can actually have a good understanding of how these actual ideas lead to the current state-of-the-art models, such as ChatGPT or GPT-4, and also other open source models. Finally, I also want to touch a little bit on the cutting-edge research topics, I would say 15%. So I want to give you a sense of what kind of research topics, especially for us, academic researchers, currently still study in 2024. And I will talk about some of the works from my group, but not in depth, but I encourage you to check out those works if you're interested. Okay, so let's just get started. So I was first part on transformers. So transformers, everyone should know that it comes from this 2017 paper, Google paper. The title is called "Attention is All You Need." Is really one of the most cited papers in the history of AI, and it's really one of the most seminal papers. So I'll start with what is attention. Actually, the idea of the attention was first introduced in this paper in 2015. The title is called Neural Machine Translation by Jointly Learning to Learn and Translate. So the idea of attention was actually first introduced in neural machine translation for the sequence-to-sequence models based on recurrent neural networks. I believe Chen, one of the authors of this paper, was actually just speaking at summer school. So the idea of attention was first introduced to actually address this bottleneck problem in the sequence-to-sequence model, and originally designed for machine translation. For example, here is one example of the translating an English sentence into a French sentence. And in the original design of the sequence-to-sequence models, you first need to go through an encoder, pass this English sentence into the encoder, and you get this one representation, the hidden state here, that summarizes all the information of the source sentence. And start from that hidden state, you start to decode like token by token. So here there is this bottleneck problem that you have to compress all the information of the source sentence into this one single vector. There is a compression. You have to do this compression and start from there. You start doing the generation and the decoding token by token. So the key idea of the attention is that instead of compressing all the information into a fixed dimension representation, here at each time step during the decoding, you just need to focus on a particular part of the source sentence. And how to focus on this, like only the relevant part or the particular part of the source sentence. So this depends on the decoders, the current state. So denoted by here the notation, the H decoder at time step T. And this can be usually implemented as a probability distribution over all the hidden states of the encoder. So here there is a notation H encoder which represents all the hidden states of the encoder, and I means the time step. So from the token 1 to the token n, that basically the length of all the hidden states on the encoder side. So just give you an example here. So here the example a little bit changed. So let's say here there is a source sentence, and then we first encode all the tokens in the on the source sentence as there are three tokens here, 3 words here. You can encode 3 words as the 3 encoded hidden states. And then now we start doing the generation. And then at the first time step, we first look at basically all the hidden states and try to figure out like which word should be more relevant for decoding the first word in the decoding. So at the first time step, then okay, the model figures out that okay, only the first token of the source word should be more relevant. Then you start to figure out okay, I should generate the word I, and the next is feeds the generated word I to the next token, to the next time step. And then you try to figure out, okay, which words should be actually more relevant. Then you figure out the second word should be more relevant. Then you start to generate the word M. And then next, find, okay, the second word and third word should be more relevant. Then generate the next word, and then we can continue and generate the word student. So essentially alignment, the attention can capture this kind of notion of the alignment. It try to learn the kind of like similarity, some notion of similarity between the source sentence and target sentence. Instead of compressing all the information into this like the bottleneck, the hidden state, it can, at every single time step, it can actually look at all the hidden representations on the source side and figure out which parts of the source sentence should be more relevant to the current target word. So this is really the kind of the key idea of the attention. And then next, I'm going to talk about some like more mathematical notations of attention and see how this actually really generalized to the attention that we have been using in the transformers. So here is still the notations of attention that we use in the sequence-to-sequence models. I already explained the notations. So here there should be like a n hidden states on the encoder side, h encoder 1 to h encoder n. And at at 10 step t of the decoder is denoted by the h decoder t as the hidden state of the decoder. Okay. So these are the notations. So the most important thing here is that after we get the all the hidden states from the encoder side and also the hidden state at the decoder side, we need to calculate this attention score, which can be basically calculated as this. Here is just a general function g. So basically, the function of g that takes each of the hidden state on the encoder side, h encoder I, and also the decoder state h decoder t, and then it can translate calculate attention score. So that basically captures the similarity between the encoder state and the decoder state. And then you normalize the attention score, and then this can convert these attention scores into this kind of attention distribution. So you can convert this ET into alpha t, which essentially just takes the softmax of the ET. So this converts this into a probability distribution, which should be an n-dimensional vector because there should be like n hidden vectors on the source sentence side. And then finally, you calculate the weighted sum of the encoder hidden states, which should just take the weighted sum. So it's summing up of the alpha I and multiplied by the hidden state encoder I. And finally, you just need to combine this output vector and also the current hidden decoder state of the current 10 step to help predict the next word. I just want to check, like, is everyone here familiar with all these kind of notations in attention? So I can move a bit fast on this part. Can you just raise your hand if you are familiar with this? Great. Oh, okay, so I'll move a bit fast. So I'll just really make sure that everyone actually knows the attention, because it's really the most important idea. So you need to calculate this kind of similarity score, attention score, and convert into the distribution. Okay, so how to think about attention? So one way to think about attention is actually to think about this as a lookup table, but it's actually a soft lookup table. So what is a lookup table? If you look at the figure on the left side, so lookup table, essentially you have like a array or table of the keys and the values. So each key can map to a single value. So if you have one query, Q, and then you just need to go to this table and look up which key should be actually most relevant to the current query. And the query matches to one of the keys. And then you get that key and then retrieve the corresponding value. And then you just return this value. So this is basically a lookup table. So the way to think about attention is just like a soft version of this kind of lookup table. So basically, you still have this table of the keys and query pairs. And then you have the query. And then you try to use the attention distribution to calculate which keys are relevant to this query. But it's not like a one-hot decision. It's not a hard decision. You need to calculate the probability distribution and figure out which keys are more relevant. Maybe this is 70% relevant. This is like 20% relevant. And then you do the weighted sum of the values and get the final output. Okay, so this is basically like the idea of the attention. So next, let's look at how the idea of the attention has been actually used in the transformers and how actually transformers generalize the idea of attention. So for most of this part, I'm going to actually look at this basic figure from the original transformer papers. And I will walk through like every single component of this figure and try to tell you how actually transformers work. So you will see the figure like many times. So this figure is actually like illustration of the transformer encoder decoder model. And this model was again proposed by Google researchers in 2017, and it was also originally designed for neural machine translation. So you can basically think of this transformer encoder and decoder as a replacement for the sequence-to-sequence model plus attention based on recurrent neural networks. So you are not going to use any recurrent neural architectures. You just use this encoder-decoder architecture to replace the sequence-to-sequence model. So just to give you like an idea of how things really, the ideas actually really evolved over the years. So the idea of RNs have been many, many decades. Even the LSTM paper was invented in 1997. The LSTM was invented in 1997. And then in 2014, the sequence-to-sequence model came out. And 2015, the paper I just mentioned, people start to add attention on top of the sequence-to-sequence model. And then in 2017, this attention is all you need paper come out. And then it shows that you don't actually need a recurrent neural network. And then you can just use the attention. And they propose this transformer encoder-decoder architecture in the 2017 paper. And since then, transformers have become basically the most popular, the default model architecture for modeling languages and even even images and other modalities. But I should emphasize that the first paper proposed the whole, like the transform encoder-decoder architecture for neural machine translation. But later on, people have been using the transformer encoders and the decoders separately for the different tasks and for different uses. But the first paper is actually like a proposal this joint model, transformer encoder and decoder. Okay, so next, let's look at this figure. So this figure is a transform encoder-decoder. The left side is the encoder, and the right side is the decoder. The encoder is basically a stack of the transform encoder layers, and the decoder is also a stack of decoder layers. As I mentioned, people have been using the transform encoder and decoder jointly and also separately. So for the transform encoder, like the models that I will also talk about in the second half of today's lecture, like BERT, Robota, and Electra, they have been all based on the transform encoder. And the state-of-the-art, like the large language models, such as GPT models, ChatGPT, Gemini, Claude, Llama, Mistral, and many other models, are only based on the decoder models. And we'll also see some other pre-trained models, like T5 BART. They are based on this transformer encoder-decoder models. And the most important, most important innovations in this 2017 papers are basically this idea of the self-attention and market-head self-attention, and I'm going to talk about this. And again, transformers don't have any recurrence structures, so it'll be just attention is all you need. It's only based on the market-head attention layers and also the feed-forward layers. Okay, so here is my plan of like walking through basically all the different components of the transformers in this lecture. So I'll first talk about what is self-attention and what is the market-head attention. And the second, I'm going to talk about feed-forward layers, and then the positional encoding, and also a little bit important tricks to make things work, including the residual connections and the layer normalization. And finally, I will put all the components together and talk about how the encoder and the decoders are different, and how this actually, how the two components are actually connected together to make the encoder-decoder architecture. And for the remaining time, I will also touch very briefly. I will also talk about some of the kind of the new modifications or architectures, the changes that have been really going into the state-of-the-art large language models, including like some new activation functions called swig glue, or some new position embedding, rotary embeddings, and the pre-normalization, and also some new attention mechanism, for example, the group query attention. So just to give you some ideas, because these are really the kind of backbone, the most the modifications have been already adapted to all the new models, at least all the open source models that we know. And finally, I also talk about some of the architecture exploration beyond transformers, but not in too much depth. And I should also mention, like after I finish the first 5, like the items here, so you should basically have a good sense of how to implement the transformers from scratch. So in the class I teach at Princeton, we actually always ask students to implement the transformers like from scratch, like based on PyTorch. So really a good reference here is actually this blog post, or also a paper called The Annotated Transformer by Sasha Rush from Cornell Tech. So I really encourage you to, if you have never really implemented transformers by yourself, I encourage you to check out this blog post and really learn how to implement this. Okay, let's get into all these different these components one by one. So first, I'll talk about the self-attention and the multi-head attention. So just want to highlight the parts here. So basically, there like the encoder side, there will be one part that is actually implemented as this attention, multi-head attention. On the decoder side, there will be actually two blocks that will be implemented using the multi-head attention. Okay, so I already talked about what is attention. So here is just a more general form of the attention. So how to think about attention? Attention is a lookup table, right? So think about the attention in a more general way. So basically, we can think about attention that as you can basically like define a set of the keys and the values denoted by K1, V1, K until K and Vn, the key value pairs. And each key vector here is a dk dimensional vector. I just, for more generality, I'll use different notations here. So each key vector is a dk dimensional vector. Each value vector is a dv dimensional vector. And here, the keys are used to compute the attention scores. And the values are used to compute the output vector. And the attention always involves the following steps. So first, I already walked through how this works in the sequence-to-sequence models. So here is just a more general form. So attention, first, you need to compute the attention score. So basically, express this attention score as a function of the query vector Q and also the key vectors Ki. And because there are n key vectors, so this attention score should be an n-dimensional vector. So basically, calculate the similarity between the Q and each key. And then you take softmax and get the attention distribution. Basically, apply the softmax on top of the E, and you get this alpha vector, which is also an n-dimensional vector. And then you use this attention distribution to calculate the weighted sum of the value. So you get the final output vector O, which should be the weighted sum of the alpha I and the VI, which should be a dv dimensional vector because it's summing up all the value vectors just with different weights. Then what is self-attention? That's a kind of general form of attention. So what is self-attention? So the key in the sequence-to-sequence models or in the neural machine translation case, the query is always the decoders, the hidden state at the current time step. And the keys and the values are all the hidden states on the encoder side. I should mention that in the neural machine translation case, in the sequence-to-sequence model case, the keys always equal to the values, but it's actually not the case in the transformers. We actually define different matrices and to get different keys and values, but in the previous case, the keys are always equal to values. So the idea of the self-attention is that take a sequence of vectors. We are going to do the attention from the sequence to itself. So here, basically, let's say if we have a sequence of words, we are going to map this sequence of words into a sequence of vectors. And then we can use each word in this sequence as a query, and all the other words in the sequence as keys and values. That's the basic idea of self-attention. As an example, you can see here, the example is a chef who blah, blah, food. So each of these words, you are going to calculate a key vector, query vector, and a value vector. And you are going to use each query vector corresponding to each word as a query, and all the other words as a keys and values. And you're going to calculate the similarity between all the other words and each single word in the sequence. So let's walk through how the attention works and then see how this works in the self-attention. So step one is we are going to first take this sequence of vectors and transform this each input vector into the three vectors, query, key, and values. So first, let's take this input vector xi, which represents the input vector at each single time step, xi, and multiply by this weight matrix wq. So wq here is, let's say the input dimension is din, and the query dimension is dq. So this wq matrix should be din by dq. And then you just multiply the input vector by this wq, and you can get the dq dimensional vector, q vector. query vector. And similarly, you can also get the key vectors and the value vectors by just multiplying the different weight matrices, WK and WV. And you have 3 sets of weight matrices, and you get 3 different sets of vectors, QI, KI, and VI for query key and value. Here is just an illustration I took from this very nice blog post that illustrates transformers. So basically, for each embedding, you can actually get a set of QKV vectors. And I should mention that here I use the row vector notion, but in many other papers, they also consider using the column vectors. So you can also write the QI as a WQ multiplied by XI here. Okay, so the second step is to compute these attention scores. So essentially, you need to calculate all the similarity between the keys and the queries, and then you need to normalize with the softmax. So here, basically for each of the query vector QI, compute the attention scores and the attention distribution by just multiply the QI, calculate the inner product between the QI and the KJ. So Q is the query vector, KJ is the key vector. And you use the inner product to capture the similarity between the query and the key. And divided by this dimension of divided by the square root of this dk is the basic dimension of this key vector. So this is also called scale dot product. Because we use this inner product to calculate similarity. So in this case, the dq must be equal to dk, just because we calculate the dot product, but it can be also generalized to other forms. So here is one example. Basically, you can calculate the Q1 with K1 and K2, and then you can basically get just 2 scores. It's probably too light here. The two attention scores, and then divided by this the square root of the dimension. So here it should be 8. Then you get these 2 scores, and then you just do the normalize and calculate the softmax. So you may want to hear, so why you actually need to do this like scale dot product? Why do you want to divide this attention score by the square root of dk? So I would say it's more or less like a more empirical choice, but the researchers find that if you don't use this square root of dk, it's actually very easy to make the dot product to become too large for the larger dk. It actually makes the optimization problem pretty hard. If you just do the normalization and divide by this, it actually makes the optimization much easier. And this also was first proposed in the transformers paper. Okay, so the third step of computing self-tension is to calculate the weighted sum, the output vector. So you basically just need to get all the attention scores and summing up over all the value vectors. So J is from 1 to N. You just do the weighted sum of the alpha ij and the Vj. And here, basically after you get all the softmax scores, and you just need to multiply by the two value vectors, because this attention score is much smaller than this attention probability, so this is much lighter here. And then finally you get this hidden repetition H1. Okay, this is actually a quiz I used in my class, but I just want to check people are following me here. So just for the example I show here, what should be the output vector for the word thinking? A, B, C, D. Yeah. So the first word is thinking, the second word is machine. And what should be the output vector for the word thinking here? Is this figure too light to see or? Yeah. I can explain. This is 112, and this is 96. This is 14, this is 12. This is 0.88, this 0.12. Yeah. I heard one answer C. What else? Sorry? B, okay. Anything else? Any other answers? Okay, the answer is C. I just want to make sure people are following me here. So these are attention scores. This divided by basically the constant. And these are actually the softmax scores. Probably two lines. This 0.88, this 0.12. So you basically need to take the probability distribution and use that probability distribution to calculate the weighted sum. So it should be 0.88 times V1 plus 0.12 plus V2 to get this final heat representation. Okay, I hope you are following me here. Okay, so this is basically the self-attention. Then next, let's look at how to basically like describe the whole calculation in the matrix notations. So earlier I used like the row vector, like the xi to represent every single vector at each input position. So here I use a matrix. So here X is a matrix, n by d in. N is basically the input length. D in is the input dimension. And then we can basically just write this as a matrix form, right? So we can get a Q matrix by multiplying the X and the WQ. So X is N by D in, WQ is D in by DQ. So as a result, the Q should be a matrix that is D in by, N by DQ. So basically each N by Q, okay, each row of the Q is actually a query vector. So similarly, you can also calculate these matrices, K and V. So each row of this matrix is a key vector and a value vector. And then you can basically calculate this attention in this form. So it's just multiplied by the two matrices, Q and the transpose of K. So Q here should be N by DQ, K should be N by DK, so transpose should be DK by N. So you calculate this attention matrix. That should be N by N. Okay, so Q times the transpose of the K and divided by this like this constant, the square root of the DK. So basically each of the element of this attention matrix, you need to divide by this constant. So you get an N by N matrix. And you apply softmax on this N by N matrix, and you still get an N by N matrix. And then multiply by this V should be N by DV matrix. Then you should get the output of this attention function should be N by DV, because N by V and N by DV, and then you get N by DV vector, N by DV matrix. So basically each row of this output matrix should be like a value, the output vector of at each single position. Importantly, I should mention that what is this actually softmax operation? So softmax is basically like you take like a list of numbers and you convert this into from a list of numbers to the probability distribution. But here is actually N by N matrix. So when you say apply softmax on top of the N by N matrix, here essentially is actually row-wise softmax. So you apply the softmax to every single row of this matrix. Not taking all the numbers in the matrix, you apply the softmax to every single row of this matrix. So here is another illustration. So basically, you multiply by these two matrices and get softmax, and then multiply V, and you get the final output vector, output matrix. Okay. So here you get a vector matrix N by N. So that means that you apply softmax at every single row, like independently. Yes, N is the number of tokens in the input sequence. Yes. Yeah. Yeah. Any other question? Go ahead. Yeah.
So just want to let everyone know the microphones are also for the others so they can hear you when you ask the question. So just raise your hand and wait for us to come with the microphone. Thank you.
I have a question, please. So here we have Q is X multiplied by YQ. So here we implicitly neglect the bias, right?
Sorry, I'm not following the question.
So to calculate the query, the key and the value,
Yes.
so we do the product between so the xi and the weight matrix.
Yeah.
And so here in this formula we neglect
Okay,
the bias.
I see.
So the question is why do we neglect it?
The question is why do we?
Why do we avoid the bias in those formulas? Because so it's calculated through a linear layer.
Yeah.
So it's next, for example, the query I is qi is xi multiplied by yq,
Yeah.
but we have bias plus bq. No, this is not the case.
I'm still not sure if we're following. So input vectors are already
Yeah, so
in
it's
the X. Yes.
yeah, it's the multiplication between x and wq.
Yes.
But we may still have a bias for each one for the Q, the key, and the value, no?
Why is there no bias?
Oh, why there is no bias?
No.
Okay. I don't have a good answer. I would say you can still also add a bias. You essentially just need to add a constant term to the input vector.
Yeah.
But yeah.
Because I usually find in papers we avoid automatically biases, but I think it's just for us, so to make the formula easier. But I still didn't find the justification why we just avoid it. That was my question.
Okay, I understand. Okay, I don't have a good answer. I haven't seen people really adding the bias to the transformer formulation. But if you want to add a bias term, you essentially just need to extend the input by adding a constant term.
Okay,
Yeah,
thank you.
I don't have a good answer yet. But can I get the use of water bottle? Yeah. Go ahead.
Hi, my question is about the WQ, WK, and WV.
Yeah.
I was wondering, so can you go into more detail how we obtain these three?
You mean how to get the QKV?
The WQ. So when you
Okay.
Yeah.
The WQ, WK, and WV are three weight matrices. Those are parameters of the transformer blocks that need to be learned from the data.
sorry, can you just repeat that? Sorry.
Okay. The X are the input vectors.
Yeah.
WQ, WK, and WV are weight matrices. Just like any other parameters in the neural networks that we need to learn those from the data.
Right, okay, so they are learned from the data.
Yes.
They're not like randomly
WQ,
initialized.
WK, WV are essentially the key main parameters of the model. Yes.
Okay, thank you so much.
Go ahead. Yeah.
Yeah, just a question. Why is it the square root of dk that we normalize with? I think I lost that information.
Yeah, basically if you don't do the normalization, and if the dimension is too large, then the inner product will become too large. Then you'll be basically dominated by the biggest values. So it's more like empirical choice. If you don't do the normalization, you'll be very, very hard to optimize, and you'll be dominated by the largest values.
Yeah, no, I understood that part, but I just don't quite understand why is the dk we normalize with and not one of the other dimensions.
dk should be equal to dv. Dk should be equal to the dq, because it's inner product.
Okay.
dq should be equal to yeah. Where is because the inner product. So actually, all these dimensions are the same eventually in all these models. Yeah.
Like dq.
dq must be equal to dk because it's the inner product. But in actually, so that's why it's actually normalized by this term, because it's the inner product between the two vectors that have the same dimension. So you normalize by the square root of the dimension of this vector. But eventually, all these dimensions are the same in the final models. Yeah.
Okay, including dv.
Yes.
Okay, thank you.
Yeah. Okay, let me move on. So I just talked about self-attention. So what is a multi-head attention, multi-head self-attention? So essentially the idea is that instead of using only one head, why not use multiple heads? So the base with many heads. So because one attention distribution or one set of attention scores essentially can capture the similarity between all the words with basically between different pairs of words. But each attention function can only focus on one set of the positions. So it's actually better to use like multiple sets of the attention functions to actually focus on the different parts of the positions. So it also gives these attention layers like multiple repetition subspace. So essentially, it's always better to do more. It allows the attention function to focus on the different parts of the positions in the different heads in this attention layer. So what does it mean? So here, let's say there is a one input matrix X here. If you have one attention head, you can basically calculate one set of the QKV matrix. And if you have another attention head, you just duplicate this. You make another separate set of the QKV matrices, and you calculate another set of QKV vectors. Essentially, for each of these, you can do this like independently. And for the attention head 0, you can get one output matrix H0 here. Let's say if you have 8 attention heads, you can basically just do this 8 times separately with totally separate sets of the QKV matrices. You can get 8 different output vectors H0 to H7. And finally, you just need to concatenate all these different heads together, and then finally apply output projection matrix to make this like the final output to like a fixed dimension. So essentially, you just need to for each of the attention head, you repeat this. You calculate this attention function x WQI, WKI, and WVI. You get the head I, the output vector for this single head, and then you just need to concatenate all these output vectors from the different heads, and then you multiply by this weight matrix WO. So here is the one illustration here. So if you get like the basically like the 8 output vectors, and then you multiply by this projection matrix, also called output matrix WO, you can finally get this one single output vector H for every single position after the multi-head self-attention layer. And but in practice, if you let's say if you use 8 heads instead of 1 head, the computation will be definitely 8 times more, right? You just do this like 8 times separately. So in practice, this is a clever design of the original transformer architecture, is that you just use a reduced dimension for each head. So let's say if for each of these original, we say their dimension should be DQ, DK, and DV. And then here we just need to, by default, let's say the hidden size is D, and the M is the number of the heads. We just need to set the DQ, DK, and DV as the same dimension of D divided by the number of the heads. And finally, WO should be also the projection output matrix should be D by D out. So this essentially gives you multiple heads, and do the repetition, calculate the repetition M times. But the total computational cost should be similar of the single head attention with a full dimensionality. So you can also just do one single head attention with a dimension D. DK equals to DQ equals to K equals to D. But you can also do this M times, and each of them should be just D by M. So essentially, each of these use a reduced dimension, and you concatenate all the heads as N, and then you would just use a similar computational cost, but it'll give you actually better representation, power or representational expressiveness compared to just using one attention head. Okay, so this basic idea, let me move to the next slide. So people actually try to understand what is different attention heads actually do. So if you look at the figure on the left, this is actually a visualization of the BERT model. And the orange lines actually denote the intensity of these orange lines basically like represent one attention head. And the green lines represent another attention head. So you can see that for this one attention head, this word eat actually aligns more to the animal. And there is another attention head that actually attends more to the content words like straight or too tired. So essentially, if you only have one attention head, you can only focus on because it only has one probability distribution. You can only focus on one part of one part of the sentence. But if you have multiple heads, the different heads can focus on the different parts of the words. So different attention heads can play a different role here. So the figure on the right here, it's basically a visualization of plotting all 8 attention heads. So it will actually becomes much harder to see what should be the role of each attention head. But it gives you this kind of some notion of interpretability, trying to understand what each attention head is doing. And by allowing multiple attention heads, they can actually play different roles in the different notion of the similarity. Okay, so finally, I just want to mention put things together. The multi-head attention, essentially, if you put everything together, this is actually can be think of just like an abstraction layer that maps input sequence x1 to xn to the output vectors h1 to hn. And if we try to stack multiple layers, you can also do the multi-head stack multiple layers of the multi-head attention. Then you can just use basically all the same dimension. So the input dimension, output dimension, and all the dimension in between the Q, K, V, and O matrices should all have the same dimension. And this actually just have the same abstraction as the recurrent neural networks. But you can just recurrent neural networks also takes in a sequence of vectors and outputs a sequence of vectors. But the multi-head attention layers essentially has the same abstraction. It also can just convert like a sequence of vectors to another sequence of vectors. But compared to recurrent neural networks, because the multi-head attention layer doesn't have any recurrent structures, so the repetitions, the calculation of the repetitions do not depend on the previous 10 steps. So they can all compute all together. You just take the whole input matrix and multiply by the weight matrix Q, K, V, and then you can just do all these kind of calculations in a parallel way. So you don't need to actually depend on the previous 10 steps. So it's actually much easier to parallelize compared to recurrent neural networks. But it's actually also more expensive to scale up to the longer sequences. I will actually talk about more later about this, because it's long context language models is really one of the most active research topics today. People try to figure out how to really scale up the transformers to longer sequences. Okay, so that's the part about the self-attention. Actually, it's also the most important part of the transformer architecture. The other parts are actually much more straightforward. So next, let's look at any questions? I see there's a question over there. Yeah.
Yeah, thank you. About multi-head, 3 short questions. One could be the sum, let's say, of the dimensions of the multi-head, of the several heads, should match, in principle, the total decay dimension or not. I split this sub k into several heads. So instead of just trying to correlate every key with every value, every query with every key, I just fix the number of keys correlated to a given query. But should I ensure that the sum of the subdimensions, sum, equals the total size, the total decay, or not? That would be the first thing. You understand? To cover basically all the space of hidden units. Yeah.
Can you hear me now? Okay.
I don't know.
Yeah, so if I understand question correctly, like basically you can think of the if we only have one attention head, so the matrix should be just one single matrix that let's say WQ should be just D in by DQ. But now because we split this into like M heads, for simplicity, you can just think of each of these, take like D by M dimension. So you can just slice the weight matrices to like M parts. So the first slice should be the first WQ matrix, the second WQ matrix, the third WQ matrix. So the sum must be equal to the original weight matrices.
Yeah, so they cover all of it, basically.
Yes, yes.
Yeah.
And then you, because you also concatenate at the end, so it be the abstraction will be exactly the same as the one attention head, but just more gives you more power to represent different parts. Yeah.
Yeah, and the second question is about well, the number of dimensions of H, let's say not of inputs, but the number of dimensions. How is that related to the input size, basically?
Yeah. Just
Wait, time.
yeah. This is a design choice, right? So DQ and DK, DV can be different from the the input vector. You can just use different numbers. But if you have to stack this to stack multiple multi-head attention, that means the output vector will be used as the input of the next multi-head attention layer. In this case, usually people just we just take the D in all the input output vector dimensions the same as the hidden repetition. So in that case, you can stack multiple layers. But the embedding vectors can be actually have a different dimension. You can also just apply a projection matrix there. Yeah. Okay, let me. I hope that answers your question. So let me move on. So in the next part, I'm going to talk about the feed-forward layers. So first, why do we need feed-forward layers? The answer is very simple. If you just stack multiple, several multi-head attention layers, essentially the model still has no nonlinearity because it's all the linear operations. So it's essentially stacking more self-attention layers. It's just doing a lot of linear projection, the re-averaging of the value vectors. So there's no nonlinearity. So the simple solution to fix this is just to add some feed-forward layers, the nonlinear layers between the self-attention layers. So this is actually very simple. So these are the self-attention layer here. After the output, after you get the output, you just apply the feed-forward layer on top of the self-attention layer. And this is actually applied position-wise, applied at each single position independently. So in the original transformer papers, they just use a very simple ReLU function. So you take the output vector xi and multiply by W1 plus a bias vector, apply this nonlinearity ReLU function, and multiply by W2 plus another bias vector D2. So I should mention there's another dimension here. It's called DFF. FF just feed-forward. Essentially, this is also usually called intermediate size in transformers. So you take the hidden size and then you multiply the feed-forward layer. You apply this to another dimension called the intermediate size, and then it's called up projection. You apply to that layer, and then the W2 should be DFF by D is a down projection. So the intermediate size can be different from the hidden size. And usually this the feed-forward size is actually intermediate size is actually larger than the hidden size. And by default, I don't know how they come up with this value, but the feed-forward dimension should be the 4 times as the hidden size. So DFF should be 4 times D. So at least in the original transformer design, but this has been changed a little bit over the years. But just want to mention that this actually uses a different dimension here. Okay, very straightforward. Okay, question there.
Two questions, please. So the first one is the MLP add the non-linearities, but with the softmax in attention, it doesn't add the non-linearity before.
No, softmax is not non-linearity, it's linear. Yeah.
Okay, thank you. And the second one is so in transformer we use one hidden layer MLP. Why?
It's one layer. Okay,
Yeah.
the question is why not use multiple layers?
Yeah, why not two layers?
I don't know, it's just cheaper. I don't know if they have experiment. I actually never seen people use multiple layers. Yeah, because it's just once a block, you have to stack multiple layers anyway. You have to stack multiple transfer blocks. So each of these has like one layer, MLP layer. But essentially, if you stack multiple layers, you still have many feed-forward layers. Yeah. But each block is only one layer. Yeah.
Okay, thank you.
Okay, so next is actually an important component of transformers called positional encoding. And why do we need positional encoding? So far, all these like architecture designs make sense. You just need self-attention, and you can just learn the similarity between all the pairs of words. But there's one important caveat here is that self-attention itself doesn't convey this ordering information. Like recurrent neural networks, you always encode the information from the left to right. So you have this kind of positional information baked in by default. But the self-attention, if you just swap the words or shuffle the words, you still learn the repetitions in the same way because you just learn the attention between this word and all the other words. So it doesn't convey this positional information. So we need to figure out a way to encode the positional information, the order of the words in the sequence in this kind of calculation or computation of the self-attention. So how to do this? The default solution is just to add some positional embeddings to the input embeddings. For example, at each single position, we also have another positional vector called PI. So also the same dimension as the input vector. So each single position, you have a distinct, different positional embedding, PI. You just need to sum up the input embedding xi and pi and make it the new input embedding. You can also choose to add the positional embedding to every single layer of this transformer architecture. But by default, people find it's just feasible or convenient to just add the positional embedding to the input layer. So you just add the positional embeddings to the input layer and stack multiple layers. And the hope is that the model should be able to capture some kind of the positional information because each position has a different positional embedding. But how are these positional embeddings implemented? There are actually many different choices. I will talk about the original design and also talk about how people actually use positional embeddings today. So the original design of in the transformer paper, you use this kind of something called sinusoidal positional embeddings. Essentially, it's actually very, I don't know how they come up with this very interesting, this sine cosine function. But each of these inside is essentially the periodic things that it considers the dimension of the vector and also considers the position of the every single of the position of the input at the position in the the sequence. So they basically use a fixed, not learnable positional embedding to capture the basically different positions have different PI embeddings. So essentially, the good thing is that this is just kind of essentially the hard-coded. It's already just baked in as a fixed embeddings, but different positions have the different embeddings. But the downside is that this is just a fixed vectors. They are not learnable. The good thing is that these are actually periodic. So people have some hope that this kind of positional embeddings, because it's a periodic, it can actually extrapolate to longer sequences. but in practice, they cannot. It's just one design choice that if you use this kind of fixed set of embeddings, and you can have, you hope these embeddings can differentiate different positions, and hope that this position embeddings can be actually used when you actually scale up to longer sequences. But actually in practice, it doesn't work so well. And another very popular choice is called absolute positional embeddings. So the idea is that instead of using the hard-coded positional embeddings, you actually treat all the positional embeddings pi from the first position to the basically max sequence length, let's say 512 or 2048, are all as learnable parameters. So you have to also learn this p matrix or the pi embeddings from the data. So you just treat this as a parameters. So this p matrix should be d by l. D is a dimension, and l is a max sequence length. So you basically treat this as a learnable parameters. You learn this from the data. And the good thing here is each position essentially can be learned from the data. You don't have to decide, okay, what should be the position embeddings like beforehand. And the downside here is that you have to set a max sequence length L. That means that if L is 2048, and you can learn the, like, say, P0 to 2047 from the training data. But if you want to use this model for longer sequences during the inference time, you don't really have the embedding for 2048, for example. So that means that you cannot extrapolate to the indices that are outside of the max sequence length. But it has been a very popular design choices. I just want to give an example, like a lot of models like BERT, GPT-1, GPT-2, GPT-3, I believe GPT-3 is, and OPT, they all use this kind of absolute positional embeddings. At the time, people haven't thought too much about longer sequence modeling. So this kind of type of the absolute positional embeddings will be actually sufficient. Give you one example here. So this from the BERT paper. I will also talk about that later. So if you see, like, the first row here is basically the input embeddings. You can ignore the second row here. And the third row is the position embeddings. So essentially for every single position, there is a basically this is a PI, so E0 to E10. So all these embeddings should be learned from the data. This is actually from the BERT figure from their paper. Okay, so any questions about positional encoding? I haven't talked about what is really what the current models, let's say Llama, Mistral, have been using, but these are kind of the positional embeddings that have been used since the Transformers paper came out, and have been actually very popular design choices using different models. Okay, so next I will just be quick and talk about some of the tricks that people have been using. And essentially, this you already should have know like how the transformer architectures really looks like. But the important thing is that transformers only work when you work very well when you stack many layers, just like many other deep neural networks in AI and like the deep convolutional neural networks. So how can people actually make the transformers really work well in practice for the very deep, like for many layers of neural networks? So there are basically like two tricks that actually important here. One is actually the residual connection. The second is the layer normalization. So if you look at the physics figure here, there are actually different components here called add and norm. So this basically the residual connection and the layer normalization has been inserted at many different positions for both the transformer encoder and the transformer decoder. So what is residual connection and what is the layer normalization? So residual connection was actually from the ResNet, the paper, very famous paper in computer vision for training the deep neural networks for computer vision. But people just use this idea also in the training the transformers. So basically the idea is if we don't add a residual connection, if the input layer is basically, like, say, the input matrix is the xi minus 1, you just go through another layer. Another layer here could be transformer or multi-head attention layer. And then you get output that is xi. But if you use a residual connection, essentially you are going to add the input vector, input matrix directly to the output matrix. So here, the xi will be the sum of the xi minus 1 plus the layer of the basically the layer applied to xi minus 1. So here essentially, if we don't need to add if we don't add this residual connection, you have to learn the transformation from the xi minus 1 to xi. But now if you add the layer, the residual connection, essentially you just need to learn the residual from the previous layer. You just need to learn what's the difference between the two layers. This is actually very important. Essentially, if you don't want to make many changes, you just need to copy from the input from this layer to the next layer. But you only need to learn the changes from this layer to the next layer. Otherwise, you have to learn basically the transformation from the one layer to another layer. And the deep neural networks have been shown to be actually very difficult to even just learn the identity function. So if you just learn the residuals, it will make the optimization much easier. And this basically prevents the network from forgetting the important information that have been already obtained from the previous layers. The next important component is the layer normalization. So basically, like the key idea here, I'm not going into much detail here, is that if you don't add a layer normalization, that means that if you are going to optimize the parameters for one single layer, and the layers that below or beneath the current layer, if the parameters are changed below this layer, that means that all the parameters in the current layer needs to be relearned. So the trick here is that you can basically just try to reduce the variation of all the hidden units from the previous layer by just normalizing all the values from the previous layers to the 0 mean and a standard deviation of 1 within every single layer. So this is actually a really common trick that have been used in many different neural architectures. So the practical formulation, what has been used in practice here is basically take all the hidden units from the previous layer, multiply by the mean of all these hidden units in this layer, and divide it by the standard deviation of all the hidden units in that layer. And there is a very small number epsilon here just to avoid like the standard deviation to become 0 in the optimization. And then finally, they also multiply by this gamma and beta term. These are two like vectors that essentially also the parameters that you need to be learned during the training. That's actually to make sure that to actually give the model more flexibility to normalize to the mean to the beta vector and the standard variation to the gamma, instead of just to like to 0 and 1. So this is actually a very common practice for now. Just to this basically how the layer normalization is actually implemented. Okay, I don't want to spend too much time on this part, but these are very important things that you should actually at least know that have been actually play a very important role to make transformers actually work in practice. Okay, so next, finally, I'm just going to put everything together to show you how the transformers encoder and the decoders work. So again, let's look at the encoder part. So encoder is just the left part of that transformer figure. So from the bottom to left to top, let's look at this. So this is the input embedding, and then we need to add the positional encoding, and each of these has a transformer encoder has n layers of transformer encoder layer, and each transformer encoder is a stack with n layers, and each of these has 2 sub layers. So one is a multi-head attention, and one is a feed forward. And in between, there are like a residual connection and a layer normalization. That's basically how the transformer encoder works. And essentially, again, this is just like one abstraction that one type of neural network architecture that can map a sequence of vectors to d in dimension to a sequence of vectors that as a d out dimension. But in most of the cases, we just specify the same dimension for the input and the output vectors. Okay, these are transformer encoders. And we have already learned basically all the components of the transformer encoder. So let's look at how the transformer decoder is actually different. So if you look at the transformer decoder, which is the right figure of the transformer encoder decoder architecture, is actually deeper, right? It has more components here. So if we look at this figure from the bottom to the top, so you first have the output embedding here. And the output embedding in the translation case is basically the embeddings for the different language, the language that you are going to translate into. And then you need to add output embedding and the position embedding. And then you just add a stack of the transformer decoder layers. And then finally, you just add a linear operation and the softmax to use to predict the next word. But the transformer decoder the stack is actually different from the transformer encoder stack. So it actually has three sublayers. I just want to emphasize this is important here. So the first layer is called mask multi-head attention. So it's self-attention, the mask multi-head attention, which is self-attention within the target sequence. That I haven't talked about this. I will talk about it in the next slide. And the next part is called multi-head attention. Essentially, this is also different from the encoder. It's actually a cross attention. It's called multi-head cross attention between source and the target sequence. So it's very similar as basically the multi-head attention on the encoder side, but this is actually used to capture the cross attention between the source and target sequence. This is actually more similar to the attention that people have been using in the sequence-to-sequence models. And then finally, in between, there is a feed-forward layers. And there are three sub-blocks of the residual connection and the layer normalization. Okay, so next, I'm just show you how this self-attention within the mask self-attention works and how the cross-attention works in this like a multi-head attention mechanism. So for the mask multi-head self-attention, so the key here is compared to the encoder. So here is a decoder. That means that you don't want the model to see the future text because you want to get a repetition and to predict the next word. If you are going to see the future words, then it's basically the information leakage. It will not help you predict the next word. So for the self-attention, essentially for every single word, you can do the attention, draw the attention between the current word and all the other words. But for the mask self-attention, it should only allow you to see the words that are up to the current time step. Let's say if the current time step is I, you should only see the words from the position 1, 2 to position I, but not all the future words. So the solution is very simple. We still do the basic calculate the attention scores as we usually do, but we are going to limit the attention to only for every single query QI, we only allow the words, this query vector, to attend to the key value pairs of J, that J is actually not more than I. So essentially, we are going to only see the only like a part of a subset of the key value vectors that appear before the current position, and also including the current position. So how to implement this? Is actually through some kind of masking. So the idea is that we just do how we do the normal attention calculation. We calculate this attention matrix as we normally do. But we are going to multiply this by a mask matrix. That means that after we get the probability, we are going to zero out all the probabilities that is actually above the diagonal of this matrix. So all these values should be 1, and all these values should be 0. That means that we are going to zero out all the attention probabilities that actually for the future context. We don't allow the current word to see the future words. And this is basically the way that we just do the attention scores, and we are going to multiply this by another masking matrix. And actually more efficient implementation is actually not to multiply by this masking matrix. Essentially, we just calculate the attention scores, but we are going to set the attention scores before the softmax that actually above the diagonal to the negative infinity. We just set all these values to be a very, very low value, very, very negative value. And then we do the softmax as we normally do. That will naturally just give you all the probabilities that above the diagonal are 0. So you just need to do the weighted sum that actually actually on this side of the diagonal to make sure that the words will not attend to the future context. So this is basically the masked self-attention that has been a very important component of the decoder. Okay, I have another quick quiz question. I want to make sure that people are actually following me here. Okay, so this is basically how the attention matrix is calculated. My question is, what should be the value of the alpha? Alpha means the probability distribution in the masked attention. So on the left is actually the raw attention scores that before the softmax. I want to ask what should be the probability distribution of the alpha 2. That means the basically this cell, the row 2 and column 2. A, B, C, D. B or D, I didn't hear that. B, yeah, you should be B. So these are the attention scores. Essentially, we are going to zero out all these attention scores that are about the diagonal. So this should be all become the very negative infinity. And then when we do the softmax, so that means for this row, this value should be 1. This value should be 1. This value should be a negative infinity. This value should be negative infinity. And we do the softmax in this row. That means that this attention probability will become 0.5. So each of these will get 0.5, and this will become 0 after the softmax. That's the idea, because you don't want to attend to the future context. Okay, the correct answer should be B. Okay, I'm definitely running out of time, so I want to finish this part before you actually take a break. So the next part is actually the multi-head cross attention. So it's basically this part. Again, the cross attention is basically the attention that between the source sentence, source sequence and the target sequence. And this is actually very similar to the attention that people have been using in the sequence-to-sequence models. This is actually pretty straightforward. I have a lot of the notations in this slide, so I don't want to spend too much time. But the key thing here is for the self-attention, essentially you start with the same input vectors. You just do the self-attention. So you use the same xi to calculate the query key and the value vectors. But for the cross attention, essentially you have 2 sets of the vectors. One set of vectors is from the encoder, and another set is from the decoder. Here, from the source side, you will always take the bit from the top layer. So let's say if you have the encoder's stack, you finish calculating all the repetitions on the encoder side. You get the repetitions from the top layer. That will be used as a hidden states from the encoder. And then you have another set of hidden states from the decoder side. So only the difference here is for the key and the value, you are going to use the repetitions from the encoder side. For the query, you are going to use the repetitions from the decoder side. That means cross attention, because you are going to draw the attention between the source and target sequence. And all the others are the same. Just instead of using the same xi to calculate QKV, you use xi to calculate qi, and the tilde xj to calculate the key and the value vectors. And the implementation are very similar. But this actually takes in the 2 sets of vectors to calculate the cross attention. And then finally, you basically get the finally you just get the value output vector to help predict the next word. Okay, so I'm done with this part. Let's just walk through how this works. So on the left is the encoder, on the right a decoder, and finally you get the repetitions from the decoder side. You apply a linear layer, apply the softmax, and you're going to use this to predict the next word. And this is just a very similar illustration of this transformer encoder decoder architecture. I just want to emphasize that for the cross attention, you always take the repetition from the top layer on the encoder side instead of taking the repetition from the middle layers. And use these repetitions to calculate the cross attention that has been inserted into the many different layers of the transformer decoder stack. Okay. this is not so important. So this is basically like how the transformer encoder decoder models have been trained, at least in the first transformer model. Again, the first transformer encoder decoder has been proposed to train on the machine translation task. So essentially, you just need to minimize the cross entropy loss on the decoder side to decode the target sequence. And then you can do the backpropagation through both the encoder and the decoder side. The training is exactly the same as how you train the sequence-to-sequence models. But here you are using the encoder decoder to train on this parallel data, which in the original paper they used 36 million pairs between English and French data for machine translation. But I also want to emphasize that the mask self-attention is really the key here, because you use a masking. So that means that you can still just calculate the attention as you normally do, because the masking, the model will not see the future words. So this can still enable the parallelism. So you can still calculate basically the loss functions at every single step for the decoder side altogether. But if you use the recurrent neural networks, you have to do this one by one. You have to calculate the current repetition, calculate the next and the next. But here you just need to calculate all the repetitions at once. By using this smart trick of the masking, then you can calculate all the loss together. So this actually makes the training much, much faster. And finally, if you look at the results from the first paper, it's good, but not so impressive as the result we are seeing today. But still, they show the transformers can already beat like the sequence-to-sequence model and also some convolutional neural architectures in this neural machine translation benchmarks in the first paper. Finally, you should probably all know the story that the state-of-the-art large language models are all based on it's only the decoder of this transformer architecture, like the GPT, Gemini, Llama, all these models. Essentially, they just take these model architectures with some modifications. I will try to talk about this after the break, but they don't have this part. Essentially, this architecture, they have the mask self-attention, but they don't have the cross-attention part because it's only the decoder. And then you have the feed-forward layer, and then you stack many layers, and you are going to only use a decoder to train the next word, to predict the next word. So you always take the current word, predicts the next word, current word predicts the next word, and you don't have the cross attention part, but the architecture is pretty much like this. And but the model the size of these models have been actually changed a lot. In the first 2017 paper, transformer papers, as you can see, the first N is actually the uppercase N here is the number of layers. So the model architecture has 6 layers. And the hidden dimension is 512. So here, D model is basically D I used in my previous slide. Hidden dimension is 512. The intermediate size is 4 times of the hidden size, is 2048. And they use 8 heads. And the dimension of each head should be 64. That the 512 divided by 8. But if you look at the GPT-3 models, the largest GPT-3 model has 175 billion parameters. Actually, I think this is like hundreds of millions parameters. I cannot remember the exact number here. But here is 175 billion parameter and 96 layers. The hidden dimension is way bigger, is 12,000 and 96 heads. And each of the head, the dimension of each head is actually still small, it's only 128. So the models have become very, very large compared to the first transformer papers, but still the model architecture hasn't been changed too much. There are some modifications I will talk about after break, but most of the architecture still remains the same, but the models have become much larger. Should I take a break right now, or I have a few slides maybe? Can I finish the, okay. Yeah, we're over time. Let me just finish the next few slides and we'll come back to this after the break. So the transformers compared to the previous generation of recurrent neural networks. The most first, because it calculates the attention between every pair of the words, so it's actually much easier to capture the long-range dependencies. As I said many times, it's actually much easier to parallelize just because you can calculate all the repetitions all at once. But there are also some downsides or some key research questions that people have been asking over the years. The first, are the positional embeddings enough to capture position information. Can we design better position embeddings? Because if we just learn a representation for every single position, it seems to be very simplified. This representation is really enough. Otherwise, self-attention will not capture any position information. And another really important thing is this self-attention needs to calculate this n by n matrix. N is the number of the tokens, the input of the sequence length. So this computation is actually quadratic with the sequence length. So for the orange, the first paper, it only works on the sequence level machine translation, so it's not a problem. For like BERT model, the sequence length is 512 words, so it's still not a big problem. But when the sequences become very long, this can be actually very slow, this quadratic attention. Actually, I have some computational analysis here. Just want to give you some sense here. If you do this offline by yourself, if you do the calculation of the self-attention, the time complexity should be nd squared plus n squared d. The nd squared is basically the first the linear projection. Is nd squared. N is the sequence length, d is the hidden size. But if you calculate the attention, it should be n squared d, because you have to calculate the inner product between like every pair of the query and the key vectors. And for feed-forward layers, it's actually nd squared. Here I use d squared because I assume that DFF is actually the same level of d. But DFF, as I said, is usually 4 times as d. So it's actually much bigger than d, but I just, for simplicity, is a constant. So I just write the complexity of the feed-forward layers as nd squared. So if you look at this, there's the trade-off here, right? If n is very large, then the complexity will be dominated by the multi-head attention. But if the n and the d are similar, so basically the multi-head attention and the feed-forward layers will be like a similarly efficient. I also want to mention actually recurrent neural networks. If we don't consider constant, like LSTM has a lot of the different components. If we don't consider constant, our recurrent neural networks only require the nd squared time. But still, recurrent neural networks are actually much slower, just because you cannot parallelize the operations. You have to do this one token by token. Let me check. Okay, let me just finish this slide then. Yeah. But how to think about the time complexity is really important here. So there's a really nice analysis here, the profiling here. If you only look at the BERT side model, what does that mean? N, the sequence length is at most 512 tokens. The hidden size is 768. And the intermediate size is 4 times of the hidden size. They actually find that self-attention is actually basically the feed-forward layers actually take 2/3 of the total number of parameters. It's actually the big part is actually feed-forward layers, not the self-attention layers. But if you consider the running time, for the BERT side models, the self-attention layer and the feed-forward layers, they take a basically equal time on GPUs. But on CPUs, actually feed-forward layers will be actually become even slower, would be actually become the bottleneck. So actually, there are a lot of pruning work or model compression work that have been trying to optimize the speed up of these models. But actually, feed-forward layers actually even slower than the multi-head attention layers. But the situation would be changed if the sequence becomes really large. At that time, people didn't consider like sequence length like 50,000. But if the sequence length become really large, like 50,000, or today, like Gemini claims that they can scale up to 1 million tokens. That really means that the computation will be actually dominated by the self-attention, which should be involves this quadratic computation. Okay, I think and there are lots of solutions have been trying to address this problem. And the long context language modeling today is a very important research topic. I think I'm just going to take a break here as to have some parts of transformer, and I will come back to this and after the break. Yep.
Okay, so we are about to begin. So if you can please quickly take a seat. Thank you.
Shall we just get started? Okay, welcome back. Okay, so in the previous part, I'm done with telling you all about the basics of transformers architecture. So next, I'm going to spend a little bit of time telling you more about the some advanced techniques that have been used in the state-of-the-art large language models, and also what people have been thinking about advancing transformers. But actually, because I still have another part on the pre-trained language models, it's very ambitious for me to finish all the content. So for this part, my plan is to go over the content pretty fast. Honestly, for each of these techniques, I can spend like 10 minutes on each of them. So my goal is really just to tell you what people have changed in these model architectures. If you want to delve into the details of these different components, I basically encourage you to do this offline. But I will tell you the high-level ideas. And then we can move on to the pre-trained language models part. Okay, so transformer architecture, as I said, was proposed in 2017, and the major components have been actually really retained like until today. So basically, all the state-of-the-art large language models have been building on top of the transformers. So what has some kind of major modifications that people have done over the years? There are actually not too many, but I will just tell you some ideas. So the first part is actually the activation function. The first transformer paper used the ReLU function to do for the feed-forward layers. But today, I would say most of the latest large language models actually use this new activation function called sweet glue. I'm not going into detail, but the idea here is sweet glue is a new kind of activation function that combines the Swiss function and also this called some gated linear unit, the GLU. So you can basically write this, basically put a sweet glue in this kind of formulation. And I put a diagram here which shows what the kind of squish function looks like. It's actually the x times the sigmoid of the beta x. Beta is just a constant here. And on the right is actually the gated linear unit. So the idea here is that for the same representation, you also pass this to another matrix. Here is actually V that actually calls a gated projection matrix, and then you can multiply the two matrices. One is a gated representation, another is original representation after some transformation, and then you do the element-wise multiplication, and you get this representation. And then you use a switch function to replace the sigmoid function. If you're interested in learning more, I basically encourage you to check out the links I put here. So the sweet glue was proposed in this paper in 2020. In their paper, they actually did a lot of exploration of different activation function from the glue switch and to this sweet glue. They basically find that the sweet glue still basically outperforms the best among all these variants. And this sweet glue activation has been used again in many of the latest models like Llama. I think it starts from Palm and definitely like Gemini, all these models. And one thing I should mention here is compared to use the ReLU activation function, you just have one up projection matrix and one down projection matrix. Here, because you have like a gate project matrix, because you have the W and the V here for the up projection operation, and you still have to down project this matrix to another to the original dimension. So essentially, there are three projection matrices here used here: the up project, down project, and gate project. So it's actually the dimension of the feed-forward layers in the latest models have been also changed. Usually they change to like 4D times 2/3, just because you have three projection matrices here. And actually the Llama 3 model, they actually keep increasing this feed-forward dimension, the intermediate dimension. Honestly, I don't know how they actually pick the number at the end, but it's actually the Llama 3 has a larger intermediate side compared to Llama 2. Just give you a sense like what people have been using here. And the second major change compared to the original transformer architecture is actually the called pre-normalization, pre-layer normalization. So on the left part of this figure, actually showed is illustration of this called post-layer normalization that have been proposed in the original architecture. The idea is that you first do the residual connection, and then you add a layer normalization on top of the residual connection. But for the pre-normalization, you actually put the layer normalization before the feed-forward layer and the multi-head attention layer, and then you do the residual connection. People find this actually helps the training, stabilize the training process of these models a lot. And the people also change the basic layer normalization from the original Jimmy Bass paper to this kind of something called RMS normalization. Again, check out this if you're interested, but these are basic, have been actually already used in all the state-of-the-art models. And the third big change is actually the positional embeddings. So in the last part, I talked about the two major positional embeddings people have been using. One is using the sine cosine, the fixed position embedding, and another is to use the absolute positional embeddings. And I also talked about the pros and cons of the two types of positional embeddings. But there's still some like downside for both, or like the one is actually not learnable. And another is you cannot extrapolate to longer sequences, and you really don't have this kind of notion to capture the relative position between the different positions of the input sequence. So first, in 2018, after the transformer papers, there is a paper called proposes called relative positional embedding. Actually, T5 model uses relative positional embedding. The key idea is instead of encoding the absolute positional embeddings, so basically one vector for every single position, they try to capture this notion of the relative distance between every pair of the words. So they don't have the positional embeddings. Instead, they try to add a term that called AIJ that try to capture the relative distance between the pairs actually in this attention mechanism. And this has been actually used in T5 and some other models. And more recently, and also this is actually really like a major advanced, is something called rotary positional embeddings. It's proposed by Su et al. In 2021 in this row former paper. Again, I don't want to talk about too much details, but the key idea is that they try to rotate the positional embeddings by like a kind of one particular angle theta. If the position is at a position M, they try to rotate this embedding by like a M theta, the angle. So the good thing here is that it reserves the information of the absolute position because it knows that where this position comes from. But it also reserves the relative position information because let's say if the two words, the two tokens are only two words apart, because they always rotate with a like similar angle, like a similar angle. So the distance between the two position embeddings will keep the same if they are always two words apart. So this actually really a kind of major advance that has been used in basically all the recent models. It has been shown to outperform both the absolute and also the relative position embeddings. It's called rotary position embeddings. It's also implemented in on Hugging Face. So just check out this how this is actually implemented. Okay, the last thing I want to talk about is this something called group query attention. It's also a very straightforward idea. So for the standard multi-head attention, as I just discussed, basically for every single position, you can calculate a one query vector, one key vector, and one value vector. But how can we actually speed up this? So there's one idea called multi-query attention. The idea is very simple. So for every single position, you still calculate the individual query vector, but you use the shared one single vector that's shared across all the positions. So essentially, you only have one head for value and the key vectors, but you have M heads for the queries. So why do they do this? Why do they do this? It's just can actually speed up the inference time quite a bit because you only have one representation for the keys and the values, and it also reduces the memory storage and also the KV cache by just the number of the values and the key vectors here. So it's basically an efficient implementation, and this has been actually quite popular. And the more recent advance is something called group query attention. It's just something in between this multi-head attention and multi-query attention. Instead of just squeezing all the value and key vectors into one vector, they decide to, okay, why not we just group the tokens? And let's say for the first group, we are going to use one set of the value and key vectors. For the next group, we are going to use another set of key and value vectors. So as you can see from this figure, it's very clear. So it's basically like a compromise or is like trade-off between the multi-head attention and multi-query attention. But by doing this, you can actually reduce the KV cache and the memory storage. And this has become very popular and become one of the default design choices just for for efficiency consideration. Any quick questions about this part? I know I move really fast because these are really a lot of content, but I really want to tell you, if you want to know what like Llama models and Mistral models have been built, these are all the kind of key design choice and also the modifications that have been used in these models.
Thanks for the presentation. I just have a quick question. Here you said that the grouped query, it can compress the KV cache. So here you means the KV cache in decoder side, right?
Yes.
Okay, yeah, so that's the question, thank you.
This has been actually used all these decoder only large language models, so yeah. Okay, so next, I have a couple of slides. I just want to give you some ideas about what kind of research topics people have been thinking and also trying to advance beyond the transformers. As I mentioned at the end of the last part, one major bottleneck or the limitation of transformers is actually this quadratic computation of self-attention that makes it very hard to scale up to the longer sequences because there is O n squared D term there. So since the original transformers, there have been a lot of different efficient transformer architectures being proposed. And there is a very good survey by Ite in 2020. They try to group all these different efficient transformer models into different buckets based on the recurrence, like low rank decomposition, and also some sparse attention patterns. So I'm just going to show you some of the examples here and what kind of ideas people have been using. The first idea is actually based on the low rank decomposition. So again, the key, all these things, the goal here is try to reduce this quadratic self-attention computation. So this model is also from Google in 2020 is called Performers. So the key idea is basically trying to decompose this n by n or in L by L in their notation here matrix into like the product of two low rank dimensions, low rank matrices Q prime and K prime. So they basically can do some kind of random projection from this dimension L to like a much smaller dimension M, and then decompose this A into the Q prime and the K prime. And they have some way to actually still calculate the attention in a efficient, also approximate way, and to make things work. So they're actually a line work similar to this performance, trying to basically decompose the basic computation of this n by n matrix, attention matrix. And another kind of representative family of the models is to use the sparse attention patterns. Instead of calculating all the entries in this very big n by n matrix, they only calculate attention at some particular positions. For example, this Long Firmer from Allen Institute and the Big Bird from Google. So they use very similar ideas. So instead of doing this n square attention, you just calculate the attention at some particular position. For example, the sliding window attention or global attention means that you always attend to the first few tokens. And the sliding window attention means that you only consider the words that are actually close enough to the current word. Or you can also even just do some kind of random tokens, just randomly sample a small, tiny portion of the attention positions. And then you have an efficient way to combine these different attention patterns. And then finally, you can just use this as a way to approximate the original full attention matrix. These are all the the approximation solutions, but they serve as a way to actually reduce the computation of the full attention matrix. And another line of research tries to focus on the this kind of recurrent structure of the segment level recurrent structure to do the long context modeling. So this famous paper called Transformer XL, the idea is basically try to, if you have a very long context, the idea is try to segment this context into multiple segments. And then you do this language modeling, like segment by segment. And then you try to cache all the previous hidden repetitions as the extended content, but you don't do the bifurcation to those repetitions. So you do the sliding window, segment by segment, cache the previous repetitions, and try to attend to the previous repetitions as like extended context. This is one effective way of the caching, extending to much longer context. I know I go really fast, so I just want to give you some ideas of what people have been doing. Also, just some quick plug here. My group has been also doing actually quite a lot of the model architecture exploration for like the long context language modeling. So in EMLP 2022, we had this paper called Chen, training language models with memory augmentation. So the idea is also try to put the repetitions from the previous long context in some kind of data store. And then there's a way to actually retrieve the relevant data store, information from the data store to actually model the long context information. And the last year, we had this paper called auto compressors. The idea is also to do this kind of recurrent structure, but we are trying to compress the long context into a fixed number of the prompt vectors. And then this set of prompt vectors can be carried over to the next segment. And you can do this like segment by segment to actually scale up to a very long context. So we did experiments with Llama 2 models, and then we are able to scale up to like 40,000 tokens in such an approach. And then finally, this year, we also had another paper that will be presented in 2 months at ACO called Long Context Language Modeling with Parallel Context Encoding. So the idea is try to encode the previous context using some kind of encoder-decoder structure, but it's a much cheaper encoder. And this also provides a way to extend the context into a much longer context by just encoding the previous context information using this encoder-decoder structure and then insert it into the decoder architecture. Again, I mainly just want to show you some kinds of ideas that we have been also thinking about. So if you are interested, I basically encourage you to check out our papers. But one important remark here is the regular retrieval augmentation is also a very active research topic these days. So for all the 3 papers I just described from my group, we actually find that the architectures and the techniques that we think about actually can generally applicable to both the long context modeling and also retrieval augmentation. We definitely see a more and more synergy or some kind of unification between the long context language modeling and the retrieval augmentation. I think it's a very interesting research area to work on, to think about what kind of architectures that can combine all both applications and also this kind of the how to extend the context of these transform models. Okay, so finally, I want to make some remarks on the all these kind of developments of efficient transformers. As I mentioned, like the e-taste survey in 2020, there has been a lot of explorations around 2019, 2021 that to propose all different kinds of the approximation solutions to replace this full quadratic full attention matrix. But honestly, more recently, especially this kind of big model development from industry, very few techniques have been actually adopted in the state-of-the-art large language models. State-of-the-art large language models are still mostly focused on using the full attention matrix. But there's one exception here, the Mistral model actually uses a sliding window attention to handle longer sequence. So they only consider the basic attention entries that actually cause that within the like fixed window size. So still, even for the, I think the reason is just because you have to, if you do the approximation for efficiency, you have to compromise the performance quite a bit. So there is always trade-off. Just more recent state-of-the-art developments of the long contact transformers to still do the full attention instead of this kind of approximation. Still, you can actually, even the models are trained using the full attention, you can still do such approximations only during the inference time. You can still take a model that trained with full attention and use this kind of sparse attention or the low rank decomposition only during inference time, and to speed up the deployment of these models, which is still also a very important research question. And I also want to mention, on the other hand, there are actually also many system level advancements have been actually proposed to scale up transformers to longer sequences without using any approximation. The most famous example is flash attention by Chen at Stanford, who will be joining Princeton faculty actually this year. And there are also a lot of other techniques, like, for example, the sequence parallelism and many other techniques that, that have been actually really proposed to speed up this process. So people still use the full attention these days, but they can actually scale up to much longer sequences compared to a few years ago. Very quick note that the transformers have been not just using modern languages, even for the computer vision, people have been using the vision transformers a lot for modeling images. I'm not going to talk more about this. And finally, I want to mention another really major development in the last couple of years, actually the mixture of expert models. So compared to the original transformer architectures, the key difference here is, so on the left is basically the, in the standard transformers, we have the multi-head attention layer, followed by the feed-forward layers, followed by multi-head attention layer. But you can actually replace the feed-forward layers by a mixture of expert model. The idea here is basically try to have like multiple experts. Let's say if you have like M experts, you can basically scale up. You can actually make the number of parameters of the in these models by M times the feed-forward layers. People only do this in the feed-forward layers, but during the inference time, only one or two of the experts will be chosen. So it will not affect the inference time much. Basically, the inference time will be similar as the standard transformers, but because these models have way more number of parameters, so it actually give you much more power or expressive power to actually make these models much stronger. And but the key, there are also a lot of other questions that you need to think about how to design the model architecture of the mixture of experts. For example, how should we choose the right experts to actually route to the right experts to actually make the predictions? And how should we train such a mixture of expert models? And I should just mention another paper from my group this year. It's called Lorry. And this is actually a new model architecture that actually is fully differentiable. So compared to the conventional mixture experts, the idea here is that essentially it's also similar to something like attention. We still use all the experts models, but through some kind of routing, soft routing. And we just do the weighted average of all the feed-forward parameters. And then we get one merged feed-forward layer. And then you pass this to the next layer, the multi-head attention. And this would actually work much better compared to the standard. Other mixture of the experts that actually require discrete routing. But this is actually a soft version because essentially you just need to learn. You still use all the feed-forward parameters, but you do the soft merging. I know this is very fast. I just want to give you a sense about what kind of things we are thinking about these days. And I still have another part. Before I go to the next part, I want to pause and see if there are any questions about architectures, because I'm not going to talk about any architectures in the next part. It's all about the pre-training. Yeah. Okay, I see your question there. Yeah.
Hi, I was just wondering, how does this apply to, for instance, audio and video? You mentioned images, but what about, just briefly, what we've been seeing in terms of sound and video? Just very quickly, thanks.
Yeah, I'm not an expert, but I have seen, for example, something like a music transformer, people try to discretize the input and do something similar as language modeling. But I also have seen people take the speech data as like the continuous input and feed that as basically like a vision transformer takes a continuous input. Yeah. But I have never worked on actually on speech data, so I cannot say too much. Yeah.
Hi, thank you for your talk. I'm just wondering about retrieval augmented large language models. So you mainly talked about non-context, but how is it also relevant to privacy and safety or ethics alignment in this kind of field? Because I imagine if you do input attribution to use retrieval augmentation, it's, yeah, just what's your take on this?
So, first, there is some language. For the context or length of the language model having in law. So people argue that maybe you don't need to you can just put a retrieve context in the context of language model. Happening more and more and evidence doing that. And another thing I want to emphasize is training retrieval, but the overall effort trying to scale up retrieval in language model. The idea is you have a language model and you want to have another data field, and then you have to how to better train the two components together in the retrieval and the language model. And what I want to put here is I actually find that there are a lot of techniques that can use to scale up long context and also to use to scale up the retrieval and language model actually be very similar. The techniques can be shared between the two, but the difference is actually how the data. For the long context, you have to take a very long document. For the retrieval augmented model, you have to take the input and also the retrieve packages. So the techniques is actually all here. For the three different dimensions here, they actually have.
Okay, thank you.
I was wondering, so for the techniques you mentioned, is it mostly applicable to decoder only models? And is it transferable to kind of other kinds of models? Okay. Okay. And why is that? Why is the focus on the decoder only model?
Is that better now? Okay.
Yeah.
I would say the reason is just the current state of the art models, all the decoder only models, all of these models we do not train from scratch. And let's say we take the Llama model, we take the Mistral models, we fine tune models from there. Yeah.
Okay. Okay. Thank you.
And that will be also arguably the main focus of most research today. Yeah.
Okay.
While on the topic, I've got a hot take to drop. Decoder only models don't use decoder models.
Sorry, I don't get the question. Decoder.
Decoder blocks are comprised of self-attention, masked self-attention,
Yeah.
plus cross-attention. Encoder models use self-attention.
Yes.
The decoder only models use masked self-attention and no cross-attention.
Yeah,
So
yeah,
they're
I actually have this.
closer to encoder models.
Yeah, yeah, I understand. Yeah. Yeah, I actually put here. So for the decoder only model, you only have the mask self-attention. And you don't have the cross attention, so I cross out here.
So we're closer to encoder models just with a mask.
It's more like the
decoder blocks.
encoder model, but you have the mask. Yes. Yeah. You only have one, two sublayers here. Yeah.
So in a sense, to answer her question, also like everything you use for encoder or decoder models also works for the other one.
I'm not following. Sorry.
I mean, since decoder only models actually use encoder blocks, you can also use decoder only improvements on the encoder blocks.
Okay, I see. I would say yes. Yeah, a lot of the improvements have been proposed for decoder only models should be transferred back to the encoder models. Just I haven't seen a lot of developments trying to scale up the encoder only models. I think that's the key, the main reason. Yeah. Today, the decoder-only model can be very large, but we just don't see models that are very large for encoder-decoder model or encoder-only models. Yeah. Actually, I will cover that in a minute, so I prefer to move on now. Okay, so I think I only have 1 hour to talk about pre-training. Okay, so I'll just give you some ideas, and I probably need to skip some parts. I basically broadly categorize the recent developments of pre-training into these different areas. The first is the BERT era. So the BERT is definitely one of the most important papers in the last 5 years, 6 years. And the BERT model also not actually BERT model, but the important idea here is the pre-training and also fine-tuning. And then in 2020, there is this GPT-3 paper that proposed that maybe you don't need fine-tuning, you just need to prompt the models and also use the in-context learning. And then the last 2 years has been really the era of the ChatGPT era, that people start to do something more supervised learning on top of the GPT-3 type models, like including supervised instruction tuning and the reinforced learning from human feedback. And finally, there have been a lot of developments of the open source models trying to make up this gap between the open source model and closed source models. There have been really the progress has been really fast. There have been lots of the exciting developments. So I'll see how much I can cover here, but I'm going to basically follow this structure and tell you some of the biggest ideas that have been developing over the years. So the first is the BERT era, the pre-training and fine-tuning. So the BERT stands for bidirectional encoder representation from transformers, was proposed by this seminal paper in 2019. The best paper award at NACO 2019 was proposed in late 2018, actually. So for researchers from Google. So I should mention a little bit about the timeline here. So BERT paper came out in October 2018, but actually a very similar time, a couple months before that, there were 2 important papers. One is the Elmo paper. So Elmo is another character from Sesame Street. So you can imagine BERT is actually named after the Elmo. And also the OpenAI's GPT-1 paper also came out that summer in 2018. So the difference from Elmo to GPT-1 to BERT is Elmo still uses LSTMs, and the GPT-1 uses a transformer decoder. So GPT-1 is basically the same as all the later GPT-2, GPT-3, GPT-4 paper, but it's actually much more scale. GPT-1 actually deserves a lot of credit for the idea of fine-tuning and so on. And then BERT came out in the late 2018, has been a really big thing in the field of NLP. So this line of research, BERT, Elmo and BERT, they also propose this idea called contextualized word embeddings. The idea is that for any sequence of words, you can actually apply an encoder function to this input and output sequence of the n vectors. And this is actually different from the conventional word-to-vec static word embeddings that each word has only one fixed vector. Here, the idea is that each word should have a different vector representation depending on the context. So that's how the people differ the static word embeddings and the contextualized word embeddings. And the inside the BERT is actually a transformer encoder that at this point you should actually be very familiar with this architecture. And the input representation of the BERT, as I already mentioned, here is basically the input embedding, the token embedding, and here is basically the absolute position embedding. And they also have something called segment embedding. Actually, not so important. Basically, they try to put 2 different pieces of the input. One piece is called segment A, and another piece called segment B. And they try to distinguish the 2 different segments, and they use 2 different sets of embeddings. So essentially, there are only 2 sets of embeddings, EA and EB here. And the BERT has like the orange BERT has basically like 2 architectures, BERT base and BERT large. The BERT base has 12 layers, BERT large has 24 layers. And again, each block basically like multi-head attention, self-attention, and also feed-forward layer with a residual connection and the layer normalization. So the key question is how is actually BERT trained? this is actually really one of the major contributions of the BERT. So the BERT basically takes the transformer encoder and propose a new way of pre-train such language models. So they propose basically two pre-training objectives. One is mask language modeling, and another is called next sentence prediction. So the mask language modeling, because it's the encoder model, so because so here is they wanted each word to see all the other contexts, but also to avoid information leakage. The idea is that they mask out like a fixed portion of the words, like 15%. They're going to replace those words. For example, in this example, store and gallon, they're going to replace these masked words by a special mask token. And they're going to feed this input. The man went to the mask to buy a mask of milk, and feed this into a transformer encoder, and go to basically predict these masked words. Everyone knows how BERT works here, right? Just can you raise your hand? Not everyone. Okay, good. So why is this 15% masking actually chosen? There's basically like is a hyperparameter, right? There's a design choice here. So if you only mask 50, if you mask very few tokens, that means that let's say if you only mask 5% of words, that means that every time you only actually predict 5% of tokens instead of 100% tokens. This will make the training process very expensive. But if you mask too much, let's say 80%, that actually means that most of the words are actually already masked out. You only have like 20% words left. That makes the prediction task very difficult. There is just isn't enough context to help you predict the masked words. So this is how they actually derive this 15% masking. And I should mention there is also some kind of complication here in the original BERT paper. Instead of just using all the mask tokens, they also have something called 80-10-10 corruption. So basically for 80% of time, they decide to replace the word with a mask token. And 10% of time, they decide to replace this word with another random word in the vocabulary. And another 10% of time, they just keep the word unchanged. So this actually helps reduce the discrepancy between the pre-training and the downstream adaptation. The 10% of time, they just keep the original word unchanged. But 80% of time, they still just replace the word by a mask token. And the second pre-training objective is called next sentence prediction. The idea here is they take a lot of the text, unlabeled text, and they are going to sample two segment text, let's say segment A and segment B, and just to predict whether the second segment is actually following the first segment or not. So for the 50% time, they just the max sequence length is 512 in the BERT model. They just sample a text segment of 512 tokens from the training corpus. And for another 50% time, they sample one text segment of 256 tokens. And they sample another text segment of 256 tokens from a different document. And the goal here, the next sentence prediction, is to basically predict whether this, let's say the man went to mass store, he bought a gallon mass milk, to predict this sentence is actually following this sentence. Or let's say this is a totally random sentence. Penguin masks are flightless birds, and it's not following the sequence. So the goal here is to, their hypothesis is that if they can add another pre-training objective, it can help us understand the relationship between the different sentences. Because there is a way to, the pre-training is to understand whether the second sentence is actually following the first sentence or not. And then finally, the mask language model and the next sentence prediction loss actually combined together during the pre-training process. Okay, I hope that most of you have seen this before. Otherwise, we might be too fast here. But I also want to make some notes here because BERT has been 5-6 years. So BERT was invented in late 2018. In 2019, there's a span BERT paper and a Roberta paper. They actually find the next sentence prediction objective actually not necessary. So the Roberta model actually doesn't use the next sentence prediction at all objective. And I was very actually fortunate to co-author on both of these papers. So yeah, basically we find that the only the mask language modeling is actually crucial for the performance of this kind of pre-trained models. Next sentence prediction, because if you sample 2 segments from the different documents, it also has a problem that it would actually add some noise because the 2 documents are totally irrelevant, and you still need to draw the attention between the 2 segments. So this actually adds more noise than actually benefits. And later on, robotic model basically just removed this next sentence prediction. And we also had a paper actually in 2013, last year, trying to actually understand the role of this masking rate. So why do you actually want this 15%, right? It feels like a magical number. So we wrote a paper, the title is just called 始终 mask 15% in mask language modeling. The paper was presented at ESCO last year. So we actually find that the masking rate shouldn't, 15% masking rate is actually definitely not optimal, is not a constant. So optimal masking rate should really depend on both the model sizes and also the masking strategies. Actually, you can actually adopt a much higher masking rate in larger models. But if you just train a bird-based model, maybe 15% is still very good. But if you want to train a larger encoder-only model, actually higher masking rate could be actually adopted in the larger models. And we also show that the masking actually can play 2 different roles. One is corruption, because if you mask more, you basically just make the prediction task harder, and then makes the prediction task harder, and is actually like just corrupt more, and it's harder to predict. But if you also mask more, that also means that you can get more training signal, because you can actually predict, let's say 30% or 40% of words, and that could make the training process much more efficient. So there has been actually some recent work trying to decouple these 2 factors. So trying to decouple the corruption versus prediction to actually design better training objectives to actually enable more efficient pre-training of such models. Okay, so this is about how BERT is actually pre-trained. So the next question is, how is BERT actually used for downstream task? So this actually really the most important key concept in actually BERT model, BERT paper, and also the GPT-1 paper, that you just need to pre-train once. And the same encoder model, the same model can be actually reused many times for different downstream tasks with very minimum task-specific modifications. That's really the most important concept in BERT paper. So if you just do the BERT pre-training once on the left, you can actually fine-tune this for different tasks like text classification, named entity recognition, and the question answering, and many other tasks. So just give you some examples. Say if BERT has been already pre-trained, how can we use this for text classification tasks? For example, sentiment analysis. So there's a movie review, either predicted positive or negative. The idea is actually very simple. You just add a linear classifier on top of this CLS reputation. And you essentially just need to add very minimal parameters. So let's say D is a hidden dimension of this transformer encoder, and C is the number of classes. Essentially, you just need to add like 1 linear layer on top of the CLS reputation, just introduce D times C number of parameters, 768 for BERT base times 2, new parameters. So this is actually a tiny fraction compared to the size of the BERT models. And then you can just fine-tune all the parameters of the BERT model and also the new parameters of this linear classifier together on the downstream task. In this example, sentiment analysis data set together, and then you can get a very good performance. And very similarly, this for the SCORT, Stanford question answering data set, which has been really one of the representative tasks for testing pre-trained language models, but maybe not anymore in the recent developments. But at least in the BERT era, all of these models really have been really evaluating on the SCORT and many other tasks. So this Stanford question answering task, the format is basically like given a passage of text and given a question. For example, in this example, what language did Tesla study while in school? And then you need to predict a span or segment of text in this passage, which should be the answer to this question. So the way they do this is you just need to take the BERT model, and then you get all the hidden representation at the top, and then you add 2 linear classifiers at the top. One is to predict the start position, and one to predict the end position of this answer span. So actually, the final loss could be very simple. You just need to add the 2 cross entropy loss of predicting the start and predicting the end. And by taking the the hidden rotation on the passage side, and by applying 2 linear Basel weight transformations here, by applying multiplying W start and W n, and then you can use this convert this into probability distribution, and use this to predict the start and end position of this model. So it's very simple. You essentially only add the d times 2 new parameters, and then you're going to fine tune these new parameters together with the BERT parameters, and then you can get a very good performance. And why I emphasize this is really because really, maybe you have seen this already, like after a couple years, but this at that time was a really revolutionary idea, because I actually finished my PhD in 2018. I actually did a lot of the architecture engineering type of research for question answering. So before the BERT model came out, a lot of researchers have been actually trying to design new model architectures for different tasks, different types of tasks. For example, this one model architecture for question answering. So at that time, you have to really figure out how to connect the different components to design for different tasks. But the BERT came out, and you just have one single model, and then you add 2 very simple linear layers on top of that, and then you can actually achieve way better performance compared to the previous generation of the question answering model. So that was a really big change to everyone in the community. And the one thing I should emphasize is, before the BERT came out, most of the neural question answering models basically have only 2 to 3 million parameters. But the BERT model essentially scale up the number of parameters by 100 times already. So 2 to 3 million to 110 for BERT-based model, and the 330 million number of parameters for the BERT large models. As of today, if you look at this number of parameters, it's really, really small. But at the time, the 100 times jumped compared to the pre-BERT models. So that was really a big deal and achieved very good performance. And another quick idea have been actually also people have been starting in the last couple of years called prompt-based fine-tuning. So my group has also done one of the early works in this space. The idea is also very simple. Let's say, I just told you how to actually adapt BERT to a sentiment analysis task by just adding a linear classifier on top of the sales token. But is there another way to do this? So this is basically how we usually do. So we add a sales token as a linear classifier on top of this, and then you're going to predict positive or negative. But another way you can do this is to change the input to some kind of using some template or prompt. Let's say if this input is no reason to watch, and you just add like a very simple prompt that either was mask. And you can map because you are going to predict positive sentiment or negative sentiment. You can basically map the positive to great and negative to terrible. So there's a label mapping here to predict, okay, no reason to watch, either was terrible or either was great, which one should fit better, right? In this case, you don't need to introduce like even just 2 new additional parameter, new linear classifier. You just need to reuse the mask language modeling head and just to predict whether the great or terrible should fit in this context better. You can still fine-tune all the parameters way better. You can still fine-tune all parameters all together and achieve way better performance. Just to give you one example, on the Stanford sentiment analysis tree bank, if you just do the standard fine-tuning, if you use only 32 examples, you can get 81% accuracy. If you use the whole training set, 67,000 examples, you can get almost 94% accuracy. But if you just do the prompt-based fine-tuning, if you only randomly sample 32 examples and reuse the MLM head to predict great or terrible, using only 32 examples, you can actually achieve almost 93% accuracy. So this actually also a really big, good improvement. So the key idea is just to reuse the parameters that you have been already used in pre-training. But the key design choice is how to design this label mapping and how to design this template. So in our paper, we actually explored a number of the automatic ways of doing this. So you can check out the paper. Okay, so next I'm going to talk a bit about the training cost of the BERT models. As I mentioned, the bird comes with two models, bird base and bird large. One is 110 million parameters, another is 330 million parameters. And the bird model was trained on Wikipedia and the books corpus, which has 3.3 billion tokens, which is still also tiny today. But at the time, it was a really big deal. It's a really very big collection of the training corpus that people can find actually publicly available. And at the time, like so probably you already don't, I don't know if you still use Titan V GPUs, but at the time, training on the 8 NVIDIA Titan V GPUs, it basically cost 6 days for training bird-based model and 26 days for training bird large. But today, like this is actually something called a Mosaic bird, comes from Mosaic AI in 2023, March 2023, not too long ago, like 1 year ago. They basically show that there is a lot of techniques combined, including flash attention, also including actually the much higher masking rate. I think they use 40% masking rate in Mosaic bird, and also many other system level improvements. You can actually pre-train the bird from scratch for $20. Honestly, I don't know how the $20 is calculated here, but in their title. But they show that you can actually train bird models way faster in 2023 on the 8A100 GPUs. So it's much easier compared to 2018, 2019. That was only able to be done by Google and Meta and the big companies. And I just talk about some other important models that came out at that time. And the next model is actually the Robota from Meta in 2019. This model is actually basically a replicative study of the bird model. They show that bird is still under trend. They also remove the next sentence prediction objective and train with way more data and bigger batch sizes. And they show that if we just throw in more data and train much longer, this model is just much stronger than the original bird models. So Robota model has become really popular. And just in case you didn't know, Robota was also kind of like a character in Sesame Street, but not as popular as the Elmo or Bert. So that's how the Robota name was actually come up. I also want to mention there has been also a lot of explorations at that time trying to explore the new training objectives, pre-training objectives for this kind of encoder-only models. And one of my favorite models was this called Electro from Stanford, by Stanford and Google researchers. So but their idea is just very quick. So actually they have a generator and a discriminator. And the generator is actually a smaller mask language model. So the idea here is if you take the input, let's say the chef cooked the meal, you still do 50% masking. And then you use a much smaller mask language model to predict what words you should fill in this mask token. So for example, the chef cooked the meal and predict the chef ate the meal. So you can see the is actually the same as the original word, but the ate here is actually a reasonable word, but it's actually not the same as the original word cooked. And then they're going to train this encoder model with a different objective to predict whether the word has been changed or not. So you can, here you should still predict the original. Here the original, but here the word ate is already different from the original word cook. So it has to, it's a binary classification task to predict the original versus replaced. And also an important thing here is, here the input is all natural text. So you don't have any mask token. So it actually reduces the discrepancy between the pre-training and the fine-tuning. And because you can actually perform this binary classification task to predict the word has been replaced or not. So it actually makes 100% predictions instead of only 15%. In the mask language model, you only predict which words has been, only predict the masked words. Here you can predict at every single position because you don't know which positions have been masked out. You just take this input, corrupted input, then predict whether this word has been changed or not, or has been replaced or not. So this is actually arguably a more sample efficient solution compared to the original mask language modeling. Finally, I also want to mention, I just want to say GPT-1 model is actually really important, but the GPT-1 model uses a transformer decoder, but the BERT model uses a transformer encoder with this mask language modeling. At that time, people still believe that bidirectionality is actually very important for natural language understanding task. At least in this ablation study of the original BERT paper, they show that basically this mask, this blue curve is basically the mask language modeling. This red curve is basically like GPT-1, just doing the autoregressive language model. And after you finish the training the model, you still fine-tune the model on different downstream tasks. So here the y-axis is basically the accuracy on the MNLI task. They show that the bidirectional training is still very important compared to doing this unidirectional language modeling. I'll pause a bit to see if people have any questions about BERT before I move to the encoder-decoder models. Okay, so I'll move on. So at that time, people basically like reached a consensus that bidirectionality is still very important. But the BERT models can only work for natural language understanding tasks. Because these models cannot really generate text naturally, because it is an encoder model. You cannot use this model to decode basically predict the next word. So then this comes to this natural idea. Why don't we just combine the best of both worlds? Why don't we just use both the bidirectionality of the text, but also use a decoder to generate the text in a natural way? So this basically comes to the idea of the T5 model, the text-to-text model. So T5 stands for text-to-text transformer. So it's based on this transformer encoder-decoder architecture. And the encoder is a bidirectional model, is an encoder model. So it still can be used to preserve the bidirectionality. But the decoder is a decoder-only model, is a decoder model. So you can still use the decoder for generation. And in this T5 paper, they propose a new pre-training objective, as you can see from here. The idea here is you take a segment text from the raw corpus, from the unlabeled corpus. For example, thank you for inviting me to your party last week. And you are going to mask out 15% words as what BERT does. But it's actually they did spam masking as in spam BERT. So they always mask out 15% words, but they do the continuous masking, contiguous masking. So they mask several spans of text. In total, there will be 15% of words. And then after you mask out the words, you are just going to replace these masked words into like a unique labels, identifiers like X and Y here. So these two words for inviting will be actually mapped to X. This word last will be mapped to Y. And the task is to actually predict the masked words, but in a sequential way. So if the input is thank you X me to your party Y week, the output should be X for inviting Y last Z. So this like a special symbols X, Y, Z are just trying to differentiate different spans that have been masked out. And then you are going to predict this in like a continuous, like token by token in the encoder-decoder model architecture. So in this case, you still use the encoder, bidirectional encoder to encode this context, but you can actually use a decoder to predict this word, all the masked words sequentially. So it's actually a really clever way of combining the both ideas. And during fine-tuning, T5 also has a very important contribution. They also find that instead of just adding like a classifier for natural language understanding tasks, such as text classification and question answering, they cast all the natural language understanding tasks as this text-to-text prediction task. For example, if this is like a semantic textual similarity task, and the goal is to predict just one score to capture the similarity between these two sentences, and the output is just one score, 3.8. They just cast this as a text prediction task. If the input is, let's say, this is like a grammatical judgment task, and then you just need to predict the label not accessible. And for the natural language generation tasks, such as translation or summarization, you can naturally just adapt this format, text-to-text format. The input is either like an English sentence, or the input is a document that you need to summarize, and then you just need to generate the translated sentence or the summary of the text. And so this is actually very smart. So again, you combine the best of both worlds, and you do the encoder, you have the encoder, you have the decoder by using this new pre-training objective. And the other things I want to emphasize is the T5 actually has a lot other new contributions. First, they also propose a new training corpus that's actually way larger than the models, larger than the models that bird models have been trained on. So this model is called C4. Is actually a cleaned version of the common crawl, and which consists of 34 billion tokens. If you remember the books, Wikipedia plus books, it has 3.3 billion tokens. And here is 34 billion tokens, 10 times larger. Also, another thing I want to emphasize, the T5 also comes with a very large model. The largest T5 model has 11 billion parameters. So it's also like 30 times larger than the bird large model. So T5 has actually a lot of changes in terms of both the training corpus and the model sizes, and also the pre-training objective, and it also can be adapted to both natural language understanding tasks and the natural language generation tasks. And just quickly mention, there's another very popular model that basically concurrent work called BART. And BART is very similar as T5. Slightly different objective is that they only corrupt the input, but they always predict the original sequence. I'm not going to talk more about this, but basically like they take a corrupted input, but always predict, let's say, A, B, C, D, E in this case. And this can be also cross like a different sequence, different sentences in the same document. I will pause a bit to see if I have any questions. I just have too many slides. I don't have to finish all of them. Yeah.
Just a couple of curiosities. First is how this extrapolates to languages which are not English-like. And the second question is related to how do you choose the 15% masked words? Is it just at random? Well, in fact, in the example, there was 30%. But how do you choose that words? Is it just magic, randomness?
Okay. The first question is, how do these models work for non-English languages? This is definitely one of the really important questions for the community. The current models always train actually, the bird model was only trained on Wikipedia and books corpus that has only English language. Then BERT has been extended to many other languages that basically people try to collect the publicly available data from many different languages. And the state-of-the-art large language models actually usually train on the very big corpus of many different languages all together. They actually even find a lot of really interesting things that can actually generalize between different languages. And the second question is about how 15% of us chosen. Actually, I already mentioned a little bit here that I'm sure that Google researchers have done a lot of exploration for why they pick 15%. And the basic argument is that you don't want to mask too much, but you also don't want to mask too little. And I also mentioned that we did this study to show that the 15% mask rate shouldn't be just a magical number. It should also depend on the model sizes and the masking strategies. And basically for the larger models, you really should consider a larger masking rate. And the mosaic bird model I just mentioned also use a 40% masking rate, as I mentioned. Yeah.
Sorry, I believe the question was also how do you choose the masked words? Are they random,
I see.
the strategy?
Oh, I see. Yeah, they are randomly sampled. Yeah. But there are also other masking strategies, for example, spam masking. Spam masking basically means that you want to sample like several consecutive words together. But in general, the positions are randomly sampled. But I definitely have seen work that try to use another model to predict which mask position should be actually masked. But the simple form is just to do the random sampling. Yeah. Okay, I'm just going to move on to talk about GPT-3. Okay, so next I'm going to talk about GPT-3. So GPT-3 paper came out in 2020. It's a really, really important paper. So you know the series of GPT models all come from OpenAI, and from GPT-1 to GPT-2 to GPT-3. They are all really use a very similar model architecture, that's the transformer decoder, and use the same training objective, that is the autoregressive language modeling, so left to right language modeling. So what is really new, right? So what has been changed from GPT-1 to GPT-2 to GPT-3 is really the number of parameters and also the data they use to train such models. And GPT-1 was really proposed as like a fine-tuning idea and has been also used in BERT. But after starting from GPT-2, people start to realize that maybe you don't have to fine-tune these models. You can just prompt these models. And you can prompt these models, and models can still do very well. And starting from GPT-2, people start to realize that these models finally can generate very coherent and human-like and long text. But this was actually not observed in GPT-1. So all have been changed, really just on the number of parameters or the model sizes, and also the data that you use to pre-train such models. So I put some figures here to help you understand this kind of leap from the GPT-1 to GPT-2 to GPT-3. So GPT-1, only 12 layers, 512 context length. That's basically the same as BERT. And the GPT-2 used 48 decoder the layers, and the context length is increased to 1024. And the largest GPT-2 model is 1.5 billion. And the GPT-3 further doubled the context length 2048 tokens. And the GPT-3 comes with many different sizes. And the largest GPT-3 model has 175 billion parameters. And then if you look at the data size, it has been also increased a lot from 4.5 gigabytes to 40 gigabytes to 570 gigabytes. So things have been really increased exponentially from the one generation to the next generation. And things just work magically when you scale up the model sizes and also the data sizes. And I'll just give you one example. I think GPT-2 was really a turning point to show people that you can just prompt these models with some like human written prompt and let this model generate. And they can actually generate very consistent and coherent, very beautiful, fluent text. And this, again, was not really observed in the previous generation model. Right now, today, because everyone is using ChatGPT, I use ChatGPT every day. So it's not any news anymore, right? You can always use this model to generate a big chunk of text that are very, very good. But at that time, it was a news that it can generate like large chunks of coherent text. It still has a lot of hallucination problem. It makes up the stories. It makes up a lot of random things and nonsense things. But still, just grammatically, if you look at the content, it still makes a lot of sense. And that was a really big thing. This model is 1.5 billion models. Okay, so next I'm going to talk about this phenomenon called in-context learning. This was really a new thing that only proposed in the GPT-3 paper. Also, after the basic in-context learning, people start to realize that you can actually solve all these different natural language processing tasks by just prompting the large language models. You don't have to fine-tune these models anymore. But that, after ChatGPT, it becomes also a slightly different story. Okay, so GPT-3 in-context learning. Basically, before the GPT-3, people always do this fine-tuning, as I already mentioned. People still fine-tune these models using like a pretty large supervised data sets. They use 67,000 examples for fine-tuning on the sentiment analysis task. They use 88,000 passage answer question triples to fine-tune on the question answering task. But GPT-3 shows that if you already have a very powerful, very large autoregressive language models, as large as 175 billion parameters, this model can actually already perform this sentiment analysis or question answering task using only a few examples and without any gradient updates. And these examples are only provided in the context. So that's why this paper is actually called Language Models are Future Learners. So you just need only a few examples to perform this task by just putting these examples in the context without doing any gradient updates. So this is also called in-context learning, because you only have, you don't do gradient updates, you just put examples in the context. So here is a nice example that are provided in the GPT-3 paper. So basically, if you want to solve, for example, this like a English to French translation task, you just need to put in the task description, translate English to French, and you put 3 examples: sea otter to this French translation of the sea otter, peppermint to this French translation. You just put 3 pairs of example, and then you put the word English word cheese, and then you basically expect this model to do the magic and directly generate basically the French translation of this word cheese. So this is basically the idea of the in-context learning. You just need a few demonstration examples that you can put in the model that the model can actually just learn from these demonstrations and perform the task. And this has been really a big thing, at least to practitioners, because you don't need to learn how to fine-tune these models. You just need to, all you need is just to put the models in the context. And in the GPT-3 papers, they also show that if you just scale up the number of in-context demonstrations, for the larger models, like 175 billion model, you can actually, the performance will actually increase pretty nicely with an increasing number of the demonstrations input in the in-context learning. But for the smaller model, for example, 1.3 billion model or 13 billion parameter models, if we just keep increasing the number of the demonstrations input in the context, this line is still pretty flat. So this actually called as an emergent property or emergent phenomenon that you can only observe in these very large language models. Only the model can scale up to 175 billion parameters. You can actually put in a lot of demonstrations in the context to actually observe this consistent and steady improvements for the downstream task. And you can also do something very like counterintuitive. For example, this very nice example. You can let the models do this unnatural example, an unnatural task. So arguably, these examples probably have never been observed in pre-training data. Unless I don't know if it's already there today, given this blog post is already out there. So very likely, these examples have not been observed in the pre-training data at that time. But the model can still just look at the input-output pair demonstrations and still perform this like a data formatting task in a novel ways. So this is actually very surprising finding at the time that you can just learn from the in-context examples and the model can actually do the completion and finish this task. Okay, so in-context learning was viewed as kind of emergent property, emergent phenomenon that arise in these very large language models. And after 2020, there has been a lot of work trying to understand why in-context learning happens and why this actually phenomenon actually arise from like just pre-training from the large corpus. And I'll just tell you a little bit of idea here. There are several hypotheses here. The first hypothesis is if you do this in-context learning, essentially the transformers can perform some implicit form of the gradient descent to update an inner model. There has been actually a number of theoretical work trying to understand, for example, transformers learn in context by gradient descent. They argue that transformers if you can learn from these in-context demonstrations, essentially the model are actually simulating some gradient descent updates inside this model. So essentially still doing some kind of a gradient descent in an implicit way. So that means actually a number of the theoretical work trying to characterize this kind of phenomenon. And then there is another hypothesis, and also some theoretical and empirical work. They argue that transformers essentially already learn all the knowledge that you actually need for downstream applications during the pre-training. And the in-context demonstrations will be only used to recognize which task is actually required, is triggered. So you already learned all the knowledge during pre-training. In-context learning is only used to identify which task you actually need. And there is this actually very famous paper from Se Wang Ming at the University of Washington. The title is called Rethinking the Role of Demonstrations, What Makes In-Context Learning Work. And they did a very smart experiment. The idea is, instead of like, so take the input and output pairs of, as a demonstration example in context examples, but they shuffle the output labels of these input output pairs. They just try to replace the ground truth label with another random label in the output space. They basically found that the performance doesn't actually degrade at all, very little, doesn't degrade too much if you just change the output label to another random label in the output space. So this really tells that maybe the ground truth label don't matter as much as possible. Don't matter as actually people have previously anticipated, and GPT-3 claims that this is called fusion learning. Fusion learning means that you actually still need a couple of examples to actually do this in context learning. But if the ground truth labels do not actually matter that much, that means that you actually only need the output space. You only need the input label, input examples. You don't actually need the output labels. So it has to be actually a lot of understanding around how actually in context learning works. So last year, we actually also had a paper trying to actually understand these two different roles of the in-context learning. One is called task recognition, and another is called task learning. So task recognition basically is a hypothesis too that the knowledge is already learned during pre-training. You just need in-context demonstrations to recognize the task. And the task learning means that you still need the input-output mapping. You still need to learn this new mapping, input-output mapping from the demonstrations in the in-context examples. And we actually found a really interesting finding here is we believe that ICL in context learning actually does both of these roles, the task recognition and the task learning. But only the task learning would only emerge with larger models and more demonstrations. If you increase the model size, if you increase the number of demonstrations, we found that task recognition doesn't change too much. So we have some experimental design to disentangle these two parts. But if you increase the model size and use many more demonstrations, actually task learning would actually play a bigger role compared to the task recognition. I think this would probably paint a bigger and a more comprehensive picture of these two hypotheses of understanding in context learning. I don't want to talk about this. Another really important emergent phenomenon is called chain of thought prompting that has been also proposed only after GPT-3. People find that this kind of chain of thought prompting only appears in very large language models, but not in the smaller models. Okay, I think I'm hoping to, we only 4 minutes left. So I'm really hoping to wrap up this lecture in 10 minutes. So I'll just really talk about some of the really biggest ideas after the ChatGPT. I can pause to take one question if there is any question, yeah, about the in-context learning and GPT-3. Yeah,
So you talked about prompting kind of being better than fine-tuning or working almost as good. Like, so does that mean like prompting is like trumps fine-tuning, or is there areas where fine-tuning will be a better option?
Prompting is a replacement for fine-tuning, or?
Yeah, exactly.
Okay, so I would say GPT-3 is surprising because you can do prompting to achieve very similar performance as compared to fine-tuning. But you use you don't need to do gradient updates, and you don't need to use a lot of examples. But at that time, there's still a lot of model downstream tasks. The performance actually still underperform the fine-tuning, especially for some complicated reading comprehension tasks. But I think the gap is close. These days, people do not really fine-tune on like individual tasks. But people do some kind of supervised instruction tuning and RLHF type of fine tuning. Yeah. Okay, I think it's very ambitious for me to tell you how ChatGPT works. So very, very quick, just to tell you that basically two things. There's the one is supervised instruction tuning and another in reinforcement learning of human feedback. So this is a very nice blog post trying to walk through how ChatGPT-3 model evolves over the years, evolves into the ChatGPT. And this is a very nice blog post by Yao Fu, so you can find this link here. But the main changes are the following three. The first is actually people they start to put in code data in training language models. This is actually very surprisingly effective. The code data can give the language model training, makes the language model training better, makes this model better reasoners, better at reasoning. The second is they start to put in the supervised instruction tuning. That means that they have some instructions and completions. They can actually do the supervised training on top of the unlabeled pre-training. The third thing is that they start to use this kind of reinforced learning from human feedback to actually learn from the human preference data. So we actually have, for a very long time, at that period, we actually didn't know what actually had gone into ChatGPT and what actually OpenAI researchers have done until they put out this paper called InstructGPT. You can think of the InstructGPT, the kind of older version of the ChatGPT. ChatGPT has been using a lot of similar ideas from the InstructGPT. But in this paper, they finally revealed this kind of post-training pipeline that has two parts. One is supervised fine-tuning. Another part is RLHF, super reinforced learning from human feedback. And what is supervised fine-tuning? Essentially, you have these pairs. One is the instruction, one is the response. So these pairs are human written. So for example, can you write a short introduction about the relevance of the term models in economics? And then you have a very long, coherent response that actually written by human. And they just collect a lot of data like this and just fine-tune this data on top of the GPT-3. So this is supervised fine-tuning. And then the InstructGPT paper used 13K pairs of this data, but these are all written by humans and never made it public. So we never know, basically, we never have access to such data. But in the last couple of years, the community has made a lot of effort in collecting such data. They either repurpose the existing NLP data sets, or they collect this kind of instruction and response data written by humans. It's a big, big community effort. And there are a lot of different data sets that have been collected to do this kind of supervised fine-tuning. And some of the data actually distilled from the ChatGPT, from the GPT models. So for example, Stanford has this famous model called Alpaca. Essentially, the data actually distilled from GPT models. And the instructions are also generated using some technique called self-instruct, also generated by these models. And then the next part is actually the learning from human feedback. So the format of this preference data is instruction, winning response, and losing response. So the idea here is instead of just writing the prompt and the completion pair, you have the prompt, you have two responses, and you let the human judge like which response should be a better response, should be the winning response, and which response should be the losing response. So the InstructGPT paper, they mentioned they use 33,000 prompts. And they use also human efforts, the human labelers, to actually label like which prompt, which completion should be preferred and which completion should be dispreferred. So they basically have like in-house labelers to do this very expensive task, but it's really the key to make the ChatGPT work and make the at least to the public knowledge. And I'm not going to talk about what is RLHF. But after you collect this human feedback data, basically you can apply some reinforcement learning algorithm like PPO to learn from this human feedback data. And this has been a really big topic, and people are studying like many different algorithms for how to learn from such preference data. You have to train a reward model. You have to update the policy model, and you also need to make sure that the model will not be too far away from the SFT model, the reference model. I'm going to skip this. So basically some comparison between GPT-3 and Instruct GPT. And finally, I want to mention that in the last year, the one major focus has been shifting from this kind of online optimization, like reinforcement learning, PPO, to this kind of offline preference optimization methods, such as DPO. So DPO essentially is just one method, one training objective like this to learn from the human preference data. So objective is like this. Basically, like this is basically the policy model. This is a reference model. You basically directly just learn from the preference data by just plugging in this very simple training objective, and it works out well. And DPO has become really, really popular in the last year. And the people don't because PPO training involves training multiple models, and also there has been a lot of the optimization issues to make PPO work. So people like DPO just because it's simpler and also cheaper to train. I have too much. Like just actually 2 months ago, last month, we actually also released a new model algorithm called simple preference optimization, and our key design here is that we even find that the reference model is actually not needed anymore. And you just need a very simple objective like this. You get rid of the reference model. You just add a length normalization term and add like a margin term. And then you just need to use such a simple objective to learn from the human preference data. I'm not going to tell you any details here, but we actually find that this model, this simple objective, performs way better than DPO across many different settings. So if you're interested, I encourage you to check out the paper. So we have actually one model that fine-tunes the Llama 3 8 billion model and then achieves like over 50% winning rate on Alpaca Eval 2 by just using a very simple objective called simple. And this actually works out really well. So if you haven't seen this paper, I encourage you to check out. Okay, so I'm planning to just stop here. I'm happy to take more questions about basically all this kind of language model pre-training developments. Yeah.
Thanks for your talk.
I cannot see. Oh, I see.
Yeah. Thanks for your talk. So, recently I have a question about large language model. Recently I've seen some papers trying to annotate their dataset with the large language model.
Yeah.
So I'm wondering, do you think it makes sense or not?
People do a lot of the distillation from ChatGPT to use the models to generate data, to select data. The question is, let's say if we take a very strong model, GPT-4, to distill, to generate data, then do we think that GPT-4 will be kind of the ceiling or the upper bound of such approaches? What if these models give us a lot of noise? Right now, just because the open source models still very far away from this kind of strongest closed source models. So it's still a reasonable way to do this and how to generate synthetic data, how to do the data annotation. But still, we need to think about the noise or the mistakes in this kind of generated data, and how can we actually go beyond the performance of the generated data. So there's something called weak to strong generalization. So people try to use a weaker model to actually do the data annotation to train the stronger models. I'll just give one example. Llama 3 pre-training was trained on the data that have been actually labeled by Llama 2. So that's a good example.
Okay, thanks.
Actually.
Thank you for your talk. I'm here.
Oh, sorry.
Sorry,
so very hard to see.
I have a question for the tasks when we want the model to predict a value, a numerical value. This is quite difficult with prompting because usually the model defaults just to the example you showed in the prompt, and it still is just predicting text. I was asking, is there any work more similar to what we were doing with BERT models, meaning adding a classifier or predictor on top? So instead of having the model predicting only text, it could predict real numerical values. Yeah, that's the question. Like, are there many works doing this with decoder-only models instead of the encoder-only models?
Can you hear me now?
And is there any technical limit to do this, or was it just not done?
I guess I'm not sure if people have tried this. I guess just people don't see a lot of benefits of doing this. For one single task, you add a linear classifier. Yeah, especially the current prompting can work so well on a lot of the range of tasks.
Okay, thank you.
Especially classification tasks. Yeah.
Thank you for your nice presentation. So I have very generic question. I'm here. So nowadays we have large language model like ChatGPT and Llama, Mistral. So what do you think the previous model like BERT, GPT-2, that will be useless to use in our research? We can just use the large language model like ChatGPT. What do you think about this? Because currently it's bringing a lot of research challenges. If you see using a large language model, we can just do prompt engineering. There is no such fine tuning that we were doing in the BERT or all other lower model. So what do you think about this? What would be the research direction using these large language models?
Okay, can you hear me now? Okay. I would say it really depends on the use case. I know bird size models have been still widely used in industry because the large language model decoder only models have been so large, and a lot of these models are even like behind the API. So it requires cost, right? You have to call the API and to get the output back. So I know a lot of industry products, they're still built on like a very small fine-tuned models. These models are just way smaller compared to the very large models. But also on the other hand, it has been a really important need to think about how to scale down the large language models. And people really like the smaller models, like 1 billion size models, compared to, let's say, 70 billion, 100 billion models. Yeah. I would say, like, I've seen less papers. Definitely, a lot of research topics have been shifting towards large models, but how to think about reduce the cost of these models. And also, I feel like is a very important question. I also want to mention, like, fine-tuning is kind of striking back right now because we are still need to do the supervised fine-tuning on the human preference data. This is just a very different type of fine-tuning compared to the task-specific fine-tuning with BERT. Yeah, but a lot of techniques now I can see they are actually back. Yeah.
Yep. So.
Okay.
Yeah. So it's just a question about your opinion. Oh, the last thing you said, basically, it seems that now the question is not to train the best model, but if you have got a big enough model that can generate almost any stupid thing you can think about, it could be like from an evolutionary point of view, it could be like in a priori powerful system to solve anything. But I have to educate that system. So context and prompting based learning could be like if you have all the a priori capabilities in a big enough model, then you just can use that model and progressively teach that model on how to solve problems, how to give a good number, because it applies a procedure that you have trained it to do and so on. So might we be changing the way we are facing machine learning itself? The second question is if we are moving towards a new machine learning era, in your opinion.
Okay. So the question is, what should be new after this, right? I do think the post-training and the human the alignment part is definitely not done yet. There's still a lot of exploration about how to make this model stronger and to the next level. Pre-training is pretty much already there. People are still exploring, but because we are running out of data, so pre-training is almost there. People are still doing some like relatively minor tweaks, but post-training there will be still a long way to go. How to use the right data, how to scale up the parameters data, and how to really use this model to solve very hard tasks like coding tasks, mathematics tasks, which are very important topics these days. And on the other hand, I also believe that there is a really big room for prompting as well. Most of exploration right now, I talk about here, is still just on training, and you do very simple and naive way of prompting. But like chain of thought is a good example, but people do like, for example, chain of thought, actually by one of my colleagues at Princeton, do a lot of more fancy prompting on top of that, and that there's still very big room for improving, especially on the harder task. I'm not sure if I answer your question. That's my view. Yeah.
Okay, let's take 2 more questions and then pause for lunch.
Hello. This is a question going back onto prompting. So you mentioned within context learning that the examples themselves don't necessarily matter in terms of like few shot learning and whatnot. Yeah. So we can say what's not needed for a good prompt, but what is needed for a good prompt? Because we know for like when we're prompting ourselves, it's almost like you have to find the golden prompt to get the answer you want. So I just wondered like what the features of the prompt that you think make a good prompt.
Very good question. I really don't have an answer right now. Like how to collect good prompts is a really big business, right? Sometimes I'm really amazed by how other people use the prompts like efficiently and magically. I would say it could be a really good research question moving forward.
The only research I've seen on it is to do with perplexity, like the lower perplexity prompts are better than higher perplexity prompts, which I think is quite an interesting sort of, yeah, there's not much on it.
Yeah, I agree. Yeah, I think we need to we need to do some metrics to really figure out like what prompt is good, what prompt is not good. And another thing is to maybe there's a way to further improve the current models so that the models will be more robust to different prompts. I would say that's a basic way to look at this. Yeah.
I don't understand how the decoder-only models can retain the functionality of encoder-decoder models. So this encoder models have this bidirectionality that the decoder-only models don't have. So how would that work?
Okay, so first, decoder-only model doesn't preserve the bidirectionality. Only the encoder-decoder models does, because the encoder part has a bidirectionality. Decoder models can be used to generate text. And the current state-of-the-art model, decoder-only models, don't have this bidirectionality. But because people throw in so much data and scale up the number of parameters so much, so it seems to be not a major bottleneck right now. I hope this answers the question. But it doesn't have the bidirectionality. It's always, you have to use the masking and to do the autoregressive generation. Yeah.
How does it retain the functionality of encoder-decoder models?
Functionality.
For machine translation, for example.
Oh, I see. No, I guess that. Yeah, it's basically the same interface. For machine translation, encoder, decoder, you just put the the source sentence on the encoder side and you start generating. But for the decoder only, you just put, let's say, translate the following sentence from English to French, followed by the English sentence. You put everything here in the prompt. In the prompt of the decoder only model. And then you start from there doing do the generation. So everything is put on the decoder side. nothing on the encoder side for decoder only model, but the interface will be similar. You just feed everything as a prompt. Yeah.
Okay, let's thank our speaker again.
Thanks.
Thank you very much.